Have you ever stood outside on a clear, dark night, tilted your head back, and just stared into the immense blackness dotted with countless points of light? In that quiet moment, a profound question often stirs. Just how big is all of this, and what incredible, hidden truths does the cosmos hold? It's a feeling that has captivated humanity for millennia, a blend of awe and a deep, personal curiosity about our place in the grand scheme of things. Every one of those stars is a sun, many with their own families of planets, and they are all part of a dance on a scale so vast it defies our everyday understanding. But the real story, the truly mind-bending secret that modern astronomy has uncovered, is that this universe isn't static. It isn't just sitting there. It is actively and relentlessly growing. The very fabric of space itself is stretching, carrying galaxies away from each other in a cosmic expansion that is one of the most fundamental and startling discoveries in all of science. This isn't a small, slow change. It is the defining feature of our reality, a process that dictates the ultimate fate of everything we can and cannot see. This journey of discovery is what we're embarking on together today. We're going to dive deep into the heart of this magnificent mystery, exploring 25 astounding facts about our expanding universe. These aren't just dry pieces of data, they are revelations that challenge our very perception of reality. We'll uncover how scientists first stumbled upon this incredible truth, what it means for the distant future of the cosmos, and confront some of the strangest implications, ideas that sound more like science fiction than established physics. From the ghostly echo of the Big Bang that still permeates all of space to the mysterious dark energy that seems to be tearing the universe apart at an ever-increasing rate, each fact is a piece of a puzzle that is still far from complete. This is a story of human ingenuity, of our relentless drive to look up and ask why, and of a universe that is infinitely more dynamic and wondrous than we ever imagined. So get comfortable and prepare to have your perspective shifted. We're going to take a fun, slightly informal, but always fascinating tour through the greatest show there is, the evolving cosmos. We'll move beyond simple facts and figures to touch on the profound questions they raise. What does it mean for something to expand if it already contains everything? How do we measure something that, by definition, has no center and no edge? And what does this grand cosmic narrative tell us about our own tiny, fragile, and incredibly precious world? The answers are waiting, hidden in the light of distant galaxies and the subtle whispers of the void. Let's begin this exploration and uncover the 25 astounding facts that reveal the breathtaking story of our expanding universe. Our journey into the cosmos begins with a single, monumental fact that serves as the bedrock for everything else we will uncover. The universe is not static but expanding, and this expansion is not just continuing, it is speeding up. The story of this discovery takes us back to the work of astronomer Edwin Hubble in the 1920s. By meticulously observing galaxies beyond our own Milky Way, Hubble made a startling correlation. The farther away a galaxy is, the faster it appears to be receding from us. The key evidence for this motion came from a phenomenon called redshift. Think of the sound of a siren on a passing ambulance. As it moves away from you, the sound waves are stretched, lowering the pitch. Light behaves in a similar way. When a celestial object moves away from us, its light is stretched toward the red end of the spectrum. Hubble saw this redshift in the light of distant galaxies, and it was the definitive proof that the cosmos itself is growing. Space, the very fabric that contains galaxies, stars, and us, is stretching, carrying these island universes along with it. A simple but powerful way to visualize this is to think of the surface of a balloon being inflated. Glue a few paper dots onto the balloon. As you blow more air into it, each dot moves away from every other dot. There is no center on the surface of the balloon, just as there is no center to the universe's expansion. From every point, everything else appears to be moving away. For decades, scientists assumed that while the universe was expanding, the mutual gravitational pull of all the matter within it would act as a cosmic brake, gradually slowing the rate of expansion over billions of years. The big question was whether this gravitational tug-of-war would eventually bring the expansion to a halt or even reverse it in a big crunch. Then, in the late 1990s, two independent teams of researchers made a discovery so shocking it earned them the Nobel Prize. They were studying a special kind of exploding star, a Type 1 supernova, which acts as a standard candle because its intrinsic brightness is known. By observing how dim these supernovae appeared in very distant galaxies, they could measure cosmic distances with incredible precision. What they found turned cosmology on its head. The most distant supernovae were fainter than expected, meaning they were farther away than they should have been if the universe's expansion had been slowing down. The inescapable conclusion was that the expansion of the universe is not decelerating at all. Instead, it is accelerating. Something is actively working against the pull of gravity, pushing galaxies apart at a faster and faster rate. This mysterious something has been given a name: dark energy. It is not a substance we can see or touch, but rather a property of space itself, a repulsive force that permeates the entire cosmos. Its discovery fundamentally changed our standard model of the universe, revealing that we understand only a tiny fraction of what makes up reality. Think of it like this. If you threw a ball into the air, you'd expect it to slow down, reach a peak, and fall back to Earth. The accelerating universe is like that ball, not only continuing to rise but shooting upward with ever-increasing speed, defying gravity itself. This realization that dark energy dominates the cosmic energy budget and dictates the long-term fate of the cosmos is humbling. It tells us that the universe we see, all the stars, planets, and galaxies, is just the visible 5% of a much richer and stranger reality, one whose ultimate destiny is being shaped by a force we are only just beginning to comprehend. This brings us to an equally profound and humbling reality, our second astounding fact. We don't just live in a universe, we live within a very specific, finite bubble of it known as the observable universe. This isn't the entire universe, but rather the spherical region of space from which light has had sufficient time to travel to our telescopes since the dawn of time, the Big Bang. Think of it like this: the universe is 13.8 billion years old, so the most distant light we could possibly see is light that has been journeying toward us for exactly that long, 13.8 billion years. It seems logical, then, to assume the most distant objects we can observe should be 13.8 billion light-years away, creating an observable sphere with a diameter of 27.6 billion light-years. But here's where the expansion of space throws a cosmic curveball. While that light has been traveling for 13.8 billion years, the space it has been traveling through has itself been stretching. The source of that ancient light, a galaxy that existed in the early universe, has been carried even farther away by the ongoing expansion. By the time the photons finally complete their multi-billion-year journey and land in the sensor of the James Webb Space Telescope, that original galaxy is now much, much more distant. This is why the current, actual diameter of our observable universe is a staggering 93 billion light-years. That number isn't a measurement error, it's a direct consequence of cosmic inflation and the relentless stretching of space-time. We are, in effect, at the center of this colossal bubble, but it's a center that exists for every observer in the cosmos. If you were to instantly teleport to a galaxy near the edge of our observable universe, you would find yourself at the center of your own observable sphere, also about 93 billion light-years across, with a new set of distant galaxies visible on your horizon and our own Milky Way now receding into the cosmic distance. This concept shatters any notion of a privileged central position. The observable universe is a personal horizon, a product of the finite speed of light and the age of the cosmos, unique to every point of view. Which leads to a truly mind-expanding and perhaps slightly unsettling philosophical implication. The part of the universe we can see, with its hundreds of billions of galaxies, is almost certainly just a tiny fraction of the whole. Beyond our cosmic horizon lies the unobservable universe, a realm that is, by the very laws of physics, forever hidden from our view. The light from galaxies in that region simply hasn't had enough time to reach us, and because the expansion of the universe is accelerating, that light never will. The space between us and them is stretching faster than light can traverse it. So, what is the true nature of this vaster cosmos beyond our sight? Is it more of the same, an endless sea of galaxies, stars, and planets stretching into infinity? Or could the laws of physics be different there, giving rise to realities so alien we cannot even conceive of them? This cosmic horizon is a fundamental limit on our knowledge, a gentle reminder from the universe that there are realms of existence that will remain eternally mysterious. The entirety of human history, every triumph and tragedy, every work of art and discovery, has all taken place within this one shimmering bubble of space-time, a single snapshot of a reality whose true scale and grandeur may forever elude our grasp. Now, this idea of an expanding universe naturally leads us to one of the most fundamental concepts in all of cosmology, and one that is almost universally misunderstood: the Big Bang. When we hear that name, our brains instinctively picture a traditional explosion, a single, concentrated point of superheated matter and energy violently erupting outward into a pre-existing empty void. But this mental image, while compelling, is fundamentally wrong. This brings us to our third astounding fact. The Big Bang was not an explosion in space, it was the explosive expansion of space itself. There was no central point where it all began, because the event created not just matter and energy, but the very dimensions of space and time. To truly grasp this, we need to let go of the idea of a universe expanding into something. Instead, think of the entire cosmos at its very beginning as an unimaginably hot, incredibly dense, and incredibly small realm. We're not talking about a tiny speck floating in a vast emptiness. That tiny speck was the entirety of the universe. There was no outside. Then, an event of incomprehensible power occurred, initiating a period of rapid expansion known as cosmic inflation. Space itself began to stretch and grow, carrying the nascent energy and particles along with it. A fantastic way to visualize this is with the classic raisin bread analogy. Imagine you have a lump of unbaked raisin bread dough with raisins scattered throughout. This dough represents the fabric of space itself, and the raisins are clusters of matter that will eventually become galaxies. As you place the dough in a warm oven, it begins to rise and expand. Crucially, the raisins don't propel themselves through the dough, they are embedded within it. As the dough expands, every single raisin moves away from every other raisin. From the perspective of any one raisin, all the others are receding. No raisin is at the center of the expansion. The expansion is a property of the dough everywhere. This analogy perfectly mirrors our reality. Galaxies are not flying apart from each other through space like shrapnel from a bomb. They are, for the most part, relatively stationary within the overall flow of the expanding cosmos. It is the space between them that is stretching. This is why Edwin Hubble found that more distant galaxies show a greater redshift. They are embedded in regions of space that are stretching more over the vast distance their light travels to reach us. This perspective completely transforms our understanding of the cosmos. It means that if you could rewind the cosmic clock, you wouldn't see galaxies all rushing back to a single point in space like a film played in reverse. Instead, you would see the space between every object, between every galaxy, every star, and even between the atoms in your own body, shrinking until the entire observable universe was compressed into an extremely hot, dense state. This leads to a profound and beautiful consequence. There is no center to the universe, because the Big Bang happened everywhere at once. Every single location in the cosmos can claim to be the center of its own observable universe. We are not in a special or privileged position on a cosmic outskirts. From our vantage point here in the Milky Way, it appears as though all other galaxies are rushing away from us. But if you were to instantly travel to a galaxy billions of light years away, you would have the exact same view. You would see galaxies rushing away from you in all directions, with our own Milky Way appearing as just another receding point of light. The universe, in its grand design, is profoundly democratic. This concept can be difficult to internalize because it runs so contrary to our everyday experience, where every expansion we see has a center and an edge. But the universe itself is the ultimate exception. It has no center and, as far as we can tell, no edge. It is a self-contained, dynamic entity whose very fabric is continually evolving, a reality born not from a fireball in the void, but from the spontaneous unfolding of space-time itself. Now, if the Big Bang unfolded everywhere at once, bathing the entire cosmos in that initial fireball, a fascinating question emerges: where did all that energy go? The answer is all around us, a ghostly whisper from the dawn of time that leads us directly to our fourth astounding fact. The entire universe is bathed in the afterglow of creation itself, a faint, cold radiation known as the cosmic microwave background. This is the oldest light we can possibly observe, a snapshot of the universe when it was just 380,000 years old. Before that moment, the cosmos was an opaque, searing fog of plasma, so dense that light particles, photons, were constantly bouncing off free electrons, unable to travel in a straight line. The universe was essentially a glowing, blinding brightness with no way to see through it. But then, as expansion continued, the universe cooled just enough for a monumental change to occur. Electrons combined with protons to form the first neutral atoms. In that instant, the cosmic fog lifted. The photons, which had been trapped for eons, were suddenly set free, streaming unimpeded across the universe for the very first time. And those very same photons are still traveling today. They fill every cubic centimeter of space, passing through the room you're in right now and through your own body. But the universe has been expanding for 13.8 billion years since their release, and that relentless stretching of space has had a profound effect on this primordial light. The wavelengths of those photons have been stretched enormously, shifting them from the visible, hot glare of their origin all the way down the electromagnetic spectrum into the microwave region. This is why we call it the cosmic microwave background. It's not coming from any one star or galaxy. It's the foundational backdrop to everything else. That initial searing heat of the young cosmos has been cooled by the expansion to a mere 2.7 degrees above absolute zero, which is minus 270.45 degrees Celsius. It is the ultimate cold leftover from the universe's fiery birth. The story of its discovery is a beautiful example of scientific serendipity. In the 1960s, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were working with a highly sensitive horn antenna. They were plagued by a persistent, faint static hiss that seemed to come from every direction in the sky. It was constant day and night, and they could not eliminate it. They meticulously cleaned the antenna, even evicting a pair of pigeons and scrubbing away their droppings, which they humorously referred to as a white dielectric material, but the annoying noise remained. What they had stumbled upon completely by accident was the cosmic signal of a lifetime. They were hearing the faint echo of the Big Bang itself. This pervasive glow was the predicted relic radiation that cosmologists had been searching for, and its discovery provided the smoking gun evidence that cemented the Big Bang theory as the dominant model of the universe's origin, earning Penzias and Wilson the Nobel Prize. But the story doesn't end with a simple, uniform glow. If the cosmic microwave background were perfectly smooth, our universe would be a very different and much emptier place. The early universe would have been a featureless sea of particles, and gravity would have had no lumps or seeds to work with to eventually build the magnificent cosmic structures we see today. No galaxies, no stars, no planets. The crucial breakthrough came with more advanced technology. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and most recently the Planck mission, have mapped this afterglow with exquisitely precise detail. What they revealed is a masterpiece of subtle imperfection. The sky is painted with tiny variations in temperature, minuscule fluctuations where some patches are just a few millionths of a degree warmer or cooler than the average. You can think of these fluctuations as the cosmic equivalent of a seismograph reading from the Big Bang. They are imprints of the very first density waves that rippled through the primordial plasma, the result of quantum mechanical jitters that were inflated to cosmic size in the first fraction of a second. These tiny ripples are the blueprints for everything. The slightly denser regions shown as warmer spots on the map had a little extra gravitational pull. Over hundreds of millions of years, they acted as gravitational wells, slowly pulling in more and more dark matter and gas. These seeds grew, merging and clustering, eventually giving rise to the first stars, which gathered into the first galaxies, which then formed the vast clusters and superclusters we observe in the modern universe. The entire cosmic web, the great filamentary structure of the cosmos with its vast voids and dense knots, was encoded in that subtle pattern. By studying this fossil light with incredible precision, cosmologists can read the vital statistics of the universe itself, determining its age, its composition, its rate of expansion, and its ultimate geometry with a level of accuracy that was unimaginable just a few decades ago. The cosmic microwave background is therefore far more than a relic. It is the foundational document of our cosmos, a detailed birth certificate that tells us not only where we came from, but also provides the initial conditions that dictated the evolution of everything that followed. Building on that foundation of cosmic expansion, we now arrive at one of the most humbling and disorienting facts in all of science, a realization that fundamentally reshapes our understanding of reality itself. If you were to take a complete inventory of everything that makes up the universe, every single star in every galaxy, every swirling cloud of gas, every planet, and every one of us, all of that, the entire sum of the ordinary matter we know and love, accounts for less than 5% of the total cosmos. Think about that for a moment. Everything we can see, touch, and measure with our most powerful instruments is just a tiny, visible froth on the surface of a vast, dark, and mysterious ocean. So, what makes up the other 95%? This brings us to our fifth astounding fact. The universe is overwhelmingly composed of dark energy and dark matter, with dark energy alone comprising a staggering 68% of everything. Let's break that down with a cosmic pie chart. Imagine the entire energy budget of the universe as a single whole pie. One very thin, almost negligible sliver of that pie, about 5%, is the normal baryonic matter built from protons, neutrons, and electrons. This is the stuff of chemistry, biology, and life. Another, much larger slice, about 27%, is something called dark matter. We'll explore this shadowy substance in more detail later, but for now, know that it's an invisible form of matter that doesn't emit, absorb, or reflect light, yet its gravitational pull is essential for holding galaxies together. And then, dominating everything else is the remaining 68% of the pie. This is dark energy. It is not a substance in the traditional sense, but rather a property or a force associated with the vacuum of space itself, and it is the primary driver behind the accelerating expansion of the universe that we discovered earlier. The very name, dark energy, is a placeholder for our profound ignorance. We call it dark because it doesn't interact with light or any part of the electromagnetic spectrum. and we call it energy because its most dramatic effect is to infuse space with a repulsive gravity, a kind of cosmic anti-gravity that pushes the universe apart. The leading hypothesis, dating back to Albert Einstein, is that dark energy might be the cosmological constant, a fixed energy density that is an inherent property of empty space. In this view, even a perfect vacuum isn't truly empty. It seethes with a fundamental energy, and as the universe expands and more space comes into existence, more of this repulsive energy is created, leading to an ever faster acceleration. It's a concept that turns our intuition on its head, creating more of something by literally making more room for it. However, the cosmological constant is not the only idea on the table. Another compelling possibility is that dark energy is not constant at all, but a dynamic, evolving force field that has changed over the life of the cosmos. Theorists sometimes call this concept quintessence, a name that harks back to the ancient Aristotelian idea of a fifth element beyond earth, air, fire, and water. If dark energy is quintessence, its strength could vary over time and space, meaning the fate of the universe could be even more complex and unpredictable than we currently imagine. The critical point is that we simply don't know which, if either, of these ideas is correct. Unlocking the nature of dark energy is arguably the single greatest outstanding problem in fundamental physics today. It's a mystery that cuts to the core of our understanding of gravity, quantum mechanics, and the very nature of reality. The evidence for its existence, however, is overwhelming and comes from multiple, independent lines of inquiry. The first, as we discussed, was the observation of distant supernova that revealed the acceleration. The second, crucial piece of evidence comes from that cosmic birth certificate, the cosmic microwave background. The detailed pattern of hot and cold spots in the afterglow allows scientists to measure the geometry of the universe with incredible precision. The results tell us that the universe is geometrically flat, which, according to the rules of general relativity, can only be true if the total energy density of the cosmos matches a specific critical value. When you add up the density of ordinary matter and dark matter, you fall dramatically short. The only way to make the books balance is to include that huge 68% contribution from dark energy. It's the missing ingredient that makes the geometry of our universe work. This discovery forces a profound philosophical shift. For centuries, humanity looked to the stars as the ultimate symbols of permanence and grandeur. We now understand that they are merely the visible, shimmering decorations on a cosmic stage whose structure and destiny are determined by invisible, unknown actors. Dark energy is the dominant component of our reality, the unseen hand that is writing the final chapter of the universe's story, pushing galaxies apart so effectively that, in a future trillions of years from now, any civilization looking up at the sky may see only the black, empty void of their own galaxy, with all other evidence of the cosmos having been accelerated beyond their observable horizon. The quest to understand dark energy is therefore more than an academic exercise. It is a race to comprehend the ultimate fate of everything, driven by the unsettling and magnificent realization that the universe we see is but a fleeting glimpse of a much darker, deeper, and more mysterious whole. Now, as we grapple with the enigmatic force of dark energy shaping our cosmic fate, we must turn our attention to the other great shadowy constituent of the universe, the invisible scaffolding that holds the visible world together. This brings us to our sixth astounding fact. Dark matter makes up a colossal 27% of the cosmos. Unlike dark energy, which is associated with the fabric of space and pushes things apart, dark matter is a form of matter that exerts a powerful gravitational pull, acting as the cosmic glue on a grand scale. We call it dark because it is utterly invisible. It does not emit, absorb, or reflect any form of light or electromagnetic radiation. It could be flowing through you as you watch this, completely undetectable by your senses or ordinary telescopes. Yet, we are as certain of its existence as we are of the ground beneath our feet, because its gravitational signature is written across the heavens. The first compelling clues emerged from the study of how galaxies spin. Our own Milky Way, and every spiral galaxy like it, rotates like a giant cosmic pinwheel. Based on the laws of gravity established by Newton and refined by Einstein, we can calculate how fast stars on the outer edges of a galaxy should be moving based on the gravitational pull of all the visible matter we can see: the stars, gas, and dust in the galactic center. The expectation was that stars farther from the center, like Pluto in our solar system moving slower than Mercury, should orbit at much slower speeds. But when astronomers like Vera Rubin meticulously measured these rotation curves in the 1970s, they found something astonishing. The stars on the galactic outskirts were whipping around just as fast as those near the inner regions. The galaxies were spinning so rapidly that the gravity from their visible components was utterly insufficient to hold them together. According to all known physics, these galaxies should have been flinging themselves apart, their stars scattered into the intergalactic void. The only logical explanation was that each galaxy is embedded within a massive, invisible sphere of something else, a dark matter halo, that provides the extra gravitational grip to keep everything from flying away. It's like watching a child on a fast-spinning merry-go-round who isn't holding on, yet doesn't fly off. You know there must be some unseen force, some hidden safety harness keeping them securely in place. This gravitational evidence extends far beyond single galaxies. Some of the most stunning proof comes from observing enormous clusters of galaxies, the largest gravitationally bound structures in the universe. When we look at these clusters, we often see a dramatic phenomenon predicted by Einstein's theory of general relativity: gravitational lensing. The collective gravity of the cluster is so immense that it warps the fabric of space-time around it, bending the path of light from even more distant galaxies located behind it. This creates distorted, stretched, and magnified arcs and multiple images of those background galaxies, a cosmic mirage. By measuring the degree of this lensing, astronomers can precisely map the total mass of the cluster. When they compare this total mass to the mass accounted for by the cluster's visible stars and hot gas, they find a staggering discrepancy. The vast majority of the mass, about 85% of it, is completely invisible. This dark matter forms an immense underlying skeleton for the entire cluster, a gravitational anchor without which the cluster could not hold itself together. Furthermore, sophisticated computer simulations of cosmic evolution show that dark matter is the indispensable architect of the universe's large-scale structure. If you try to run a simulation of the universe's growth using only ordinary matter, you end up with a pathetic, formless cosmos. The gravity from normal matter alone is too weak, and the pressure from radiation in the early universe would have prevented gas from collapsing into the dense knots needed to form galaxies. But when you include dark matter in the simulation, something magical happens. Because dark matter doesn't interact with light or radiation, it can start clumping together gravitationally immediately after the Big Bang. It forms a vast, invisible web of filaments and halos first. This cosmic scaffolding then acts as a gravitational trap, pulling in the normal gas. It is only within these pre-existing dark matter wells that gas can cool, condense, and eventually ignite into the first stars, giving birth to the galaxies we see today. Dark matter laid down the blueprint. Ordinary matter simply followed the plans, decorating the invisible framework with shining stars. So we know it's there, we know it's crucial, and we know it makes up over a quarter of everything. But here lies the monumental catch. After decades of searching, we still have no confirmed idea what the dark matter particle actually is. It's a humbling state of affairs for modern physics. We are surrounded by something that is 5 times more abundant than the stuff we're made of, and it remains a complete mystery. The leading theoretical candidate is a class of particles known as WIMP, or weakly interacting massive particles. These are hypothetical particles that don't interact via the electromagnetic or strong nuclear forces, but might do so through the weak nuclear force and gravity. Giant experiments deep underground, shielded from cosmic rays, are trying to catch the rare, fleeting moment when a WIMP might bump into the nucleus of an atom in an ultra-pure detector. Other experiments, like the Large Hadron Collider, are attempting to create dark matter particles by smashing ordinary particles together at nearly the speed of light. And yet another approach involves looking for indirect signals, such as the unique gamma rays or other particles that might be produced if two dark matter particles were to collide and annihilate each other in space. Despite this global, multi-pronged hunt, dark matter has so far eluded every attempt at direct detection. This persistent failure has led physicists to consider other, even more exotic possibilities. Could dark matter be made of primordial black holes forged in the first chaotic moments of the Big Bang? Or perhaps it is composed of actions, hypothetical ultra-light particles that could flow through the cosmos like a ghostly wave? The mystery only deepens the more we learn. Identifying the true nature of dark matter is not just about completing a cosmic inventory. It is a fundamental quest that could open a door to an entirely new realm of physics, potentially revealing particles and forces that have operated in secret since the beginning of time, silently orchestrating the formation of every galaxy, star, and planet, including our own. This complete lack of a central point or a boundary leads us to one of the most profound and mind-bending realities we have yet encountered. While we introduced the idea earlier in our discussion of the Big Bang, it's a concept so counterintuitive and rich with implication that it warrants its own spotlight as our seventh astounding fact. Our universe has no center and no edge. The three-dimensional space we inhabit is not expanding into anything, it is all there is. This means there is no privileged location from which the expansion began, and no cosmic shoreline where the universe ends and something else begins. To grasp this, we need to actively fight against our everyday experiences. On Earth, every expansion has a center. When a grenade explodes, shrapnel flies outward from a single point. When you drop food coloring into a glass of water, it spreads from the initial drop. Our brains are wired to look for that central origin point and an outer boundary, but the universe itself is the ultimate exception to this rule. A powerful way to visualize this is to return to the surface of an inflating balloon. But let's explore this analogy with fresh eyes. Imagine the entire universe is just the two-dimensional surface of that balloon. This surface has no boundary. If an ant were to live on this surface, it could walk forever in any direction without ever falling off an edge or reaching a wall. Now, as we blow air into the balloon, the surface stretches and expands. The ant would observe that every other ant on the surface is moving away from it. From the perspective of any single ant, it appears to be at the center of the expansion. But here is the crucial part. This is true for every ant. No ant is special. No ant is at the true center because the center of the expansion isn't on the surface at all. It exists in a higher, third dimension that the ants cannot perceive. This is a direct parallel to our situation. We are like three-dimensional ants living within the expanding fabric of space-time. We see all other galaxies receding from us, making it seem as if we are at the center, but an observer in the Andromeda galaxy or in the most distant quasar would see the exact same thing, every galaxy rushing away from them. The center of the cosmic expansion is not a location within our universe. It is a moment in time, the Big Bang, which happened everywhere at once. This realization forces us to confront the true geometry of our cosmos, a topic that has captivated mathematicians and physicists for centuries. Is the universe finite, like the surface of a sphere, but in three dimensions, or is it infinite, stretching on forever? The current evidence, most notably from the precise maps of the cosmic microwave background, strongly suggests that the universe is geometrically flat on the largest scales. In a flat universe, parallel lines never meet, and the rules of Euclidean geometry we learned in school hold true. A flat universe can, in principle, be infinite. If it is indeed infinite, then it was always infinite, even at the moment of the Big Bang. That initial hot, dense state wasn't a tiny point in space, but an infinitely large universe that was infinitely dense. The expansion then was the rapid stretching of this infinite whole, cooling and diluting the energy within it. The idea of an infinite universe is perhaps the most staggering concept the human mind can attempt to wrestle with. It means that every possible history, every variation of events, every version of you that could possibly exist, might actually exist somewhere in the vastness of an endless cosmos. It implies that there is no more universe beyond a certain point. It simply is in its entirety without end. Yet, the possibility of a finite universe without an edge is equally fascinating. Imagine a universe with a geometry analogous to the surface of that balloon, but in 3 dimensions, a hypersphere. In such a cosmos, if you could build a starship and travel in a perfectly straight line for an inconceivably long time, you would not encounter a barrier. Instead, you would eventually return to your starting point from the opposite direction, just as an airplane flying straight on Earth can circumnavigate the globe. This kind of universe would have a finite volume but no boundary or edge. The ultimate fate of the cosmos is intimately tied to this geometry. A finite, hyperspherical universe could, in theory, one day stop expanding and recollapse in a big crunch. An infinite, flat universe, dominated by dark energy as ours appears to be, points toward a very different, lonelier end, eternal expansion and a gradual cooling into darkness. The fact that we have measured the universe to be flat does not definitively rule out a finite shape. It could be like a video game map that is so vast it appears flat to us, but might still wrap around on itself on a scale much larger than our observable horizon. This is a frontier of active research, with cosmologists searching for telltale patterns in the cosmic microwave background that might reveal if light has, in fact, traveled around the entire cosmos, creating matching circles in the sky. Ultimately, accepting a universe with no center and no edge requires a profound shift in perspective. It dismantles our deeply ingrained sense of location and importance. We are not at the center of anything, nor are we on the outskirts. We are simply here at one point among an infinite or near infinite number of equivalent points, participating in a grand, dynamic evolution of space-time that treats every location with perfect equality. This cosmic democracy is both humbling and liberating. It tells us that the universe is not arranged around us, but that we are a beautiful, emergent part of its vast, interconnected whole. This understanding doesn't diminish our significance. Instead, it elevates our story to a truly cosmic scale, connecting our tiny, fragile world to the grandest narrative of all, the unfolding story of an entire reality without a center and without end. Considering the immense power of dark energy relentlessly accelerating the cosmos, it's only natural to wonder where this incredible journey is ultimately headed. This brings us to a pivotal question that touches the very heart of cosmology. What is the final fate of the universe? The answer, our 8th astounding fact, hinges on a cosmic tug of war between 2 fundamental forces, the outward push of dark energy and the inward pull of gravity. For much of the 20th century, scientists believed this battle would be decided by the universe's overall density, the amount of matter and energy packed into every cubic volume of space. This density, they theorized, would determine the ultimate geometry of the cosmos and consequently its final destiny. While our understanding has evolved with the discovery of dark energy, this framework of density still paints a powerful picture of our possible futures, ranging from a fiery collapse to an eternal, frozen silence. The first and most dramatic of these classic scenarios is the Big Crunch. Imagine a universe where the collective gravitational attraction of all matter, both visible and dark, is so powerful that it eventually overcomes the momentum of the initial expansion. In this model, after billions of years of growth, the universe would reach a maximum size, pause for a fleeting cosmic moment, and then begin to contract. Galaxies would start rushing back toward one another. The sky would grow hotter and brighter as the background radiation is compressed back into higher energies, and eventually all the stars and galaxies would merge into a searing primordial soup. The entire cosmos would collapse back down into an ultra-hot, ultra-dense state, potentially mirroring the conditions of the Big Bang itself. Some speculative theories even suggest this cycle could be endless, with a big crunch giving birth to a new Big Bang in an eternal cycle of cosmic death and rebirth, a concept known as the Big Bounce. It's a poetic and somehow comforting idea, a universe with a definite cyclical rhythm. However, for this to happen, the density of the universe would need to be so high that its gravitational pull could halt and reverse the expansion. Our measurements have shown definitively that this is not our reality. There is simply not enough matter, even including all the dark matter, to put the brakes on. The discovery of dark energy didn't just weaken the case for the Big Crunch, it shattered it, turning this dramatic finale into a scientific relic. With gravity unable to win the day, the scales tipped decisively toward expansion, leading to the fate that current evidence most strongly supports, the heat death, also known as the Big Freeze. This is not a dramatic, violent end, but a slow, quiet, and inexorable fade into darkness. In this scenario, dark energy continues to drive the accelerated expansion of the universe forever. Over trillions of years, the consequences will be profound and deeply lonely. First, the cosmic horizon will shrink. As space stretches faster than light can cross it, galaxies beyond our local group will be accelerated away, their light redshifting until they vanish completely from the observable sky. The universe will become a collection of isolated island universes. Next, star formation will cease. All the interstellar gas clouds needed to birth new stars will be used up, and the existing stars will one by one burn through their fuel and die, leaving behind cold remnants, black holes, neutron stars, and white dwarfs. Even these final embers will not last. Over almost unimaginable timescales, even the protons and neutrons that make up all matter may decay, and black holes will slowly evaporate away via Hawking radiation. The universe will approach a state of maximum entropy, a condition where energy is uniformly spread out and no more work can be done. It will become a thin, ever-cooling soup of fundamental particles and radiation, drifting farther and farther apart in an ever-expanding pitch-black void. The temperature will approach absolute zero, and all activity, all structure, and all life will become forever impossible. This is the ultimate victory of expansion, a quiet and cold eternity. But what if the power of dark energy isn't constant? This question leads us to the most terrifying of the three fates, the Big Rip. In this speculative scenario, dark energy is not the gentle but persistent force of the cosmological constant, but something far more malevolent, a form of phantom energy that actually grows stronger over time. If this were true, the acceleration of the universe wouldn't just continue, it would intensify without limit. The first casualties, billions of years before the end, would be the cosmic structures themselves. The gravitational glue holding galaxy clusters together would be overcome, and they would be torn apart. Then, as the rip draws nearer, individual galaxies would be shredded. Stars would be flung from their galactic homes into the intergalactic void. The final moments would be unspeakably violent. About 30 million years before the end, the phantom energy's repulsive force would exceed the binding energy of our own solar system, ripping planets from their stars. In the last hour, stars and planets themselves would be torn asunder. In the final instant, mere fractions of a second before the end of time, the destructive force would exceed the nuclear forces holding atoms together, and every single atomic nucleus in the universe would be explosively dissociated into a cloud of fundamental particles. Space-time itself, the very fabric of reality, would be shredded. the universe would not just grow cold and dark, it would cease to exist as a coherent structure altogether. So, which of these paths is our universe actually on? The wealth of modern cosmological data, from the detailed mapping of the cosmic microwave background to the observations of distant supernova and the large-scale structure of galaxies, all points overwhelmingly toward the heat death, the Big Freeze. The universe's geometry is flat, its density is at the critical value, and the dominant component is a form of dark energy that behaves very much like a cosmological constant. While we cannot completely rule out the more exotic phantom energy that would lead to a big rip, it is not currently favored by the evidence. Our most likely destiny, therefore, is an unending expansion that leads to a cold, dark, and empty cosmos. This knowledge can feel bleak, a prognosis of cosmic loneliness, yet there is a profound and beautiful perspective to be found in this chilling fate. It gives a powerful urgency and meaning to the here and now. Every star that shines, every planet that orbits, and every life that arises does so in a fleeting cosmic spring, a golden era of structure and complexity nestled between the fiery beginnings of the Big Bang and the unimaginably long winter that lies ahead. We are living in the universe's most vibrant and interesting epoch, a time when it is possible to look up at the heavens, understand its story, and contemplate our own place within it. The heat death is not an imminent end. It is a far future horizon that makes the brilliant, temporary dance of existence all the more precious. As we contemplate the vast, dark future of the cosmos, it's worth focusing on the magnificent structures that define its present golden age. And this brings us to a truly colossal feature of our universe. Galaxy clusters are the largest gravitationally bound structures in existence. To fully appreciate their scale, let's zoom out through the cosmic hierarchy. Our journey begins with stars like our own Sun, which are themselves massive assemblies of gas ignited by nuclear fusion. These stars gather by the billions, bound together by their mutual gravity to form galaxies. Our own Milky Way is one such cosmic island, but galaxies are rarely solitary, they are social creatures. The Milky Way and our neighboring Andromeda galaxy, along with several dozen smaller satellite galaxies, form what's known as the local group, a small galactic community held in each other's gravitational sway. Now take this idea and scale it up by a factor of 1,000. Galaxy clusters are the next and ultimate step in this gravitational assembly line. They are metropolises of the cosmos, containing anywhere from hundreds to many thousands of individual galaxies, all swarming around a common center of gravity. These are not just random, loose collections, they are dynamic, densely packed environments. A rich cluster can contain a staggering amount of mass, often a million billion times the mass of our Sun. But here's the crucial part we've learned from our earlier discussions. The galaxies you see in a Hubble Space Telescope image of a cluster, those beautiful, swirling spirals and glowing ellipticals, are merely the visible tip of a much deeper iceberg. They are like a few glittering lights on the surface of a dark, massive ocean. The true bulk of a cluster's mass, as much as 85% of it, is in the form of the dark matter halo that envelops the entire structure, providing the immense gravitational well that keeps everything together. Furthermore, the space between the galaxies isn't empty. It's filled with a superheated, tenuous gas known as the intracluster medium. This gas is so incredibly hot, tens of millions of degrees, that it glows not in visible light but in powerful X-rays. In fact, this hot gas often contains more normal matter than all the stars in all the cluster's galaxies combined, making the brilliant galaxies themselves almost an afterthought in the total mass budget. But galaxy clusters are far more than just isolated cosmic cities. They are the fundamental building blocks of the largest structure we have ever mapped, the cosmic web. This is the grand, overarching architecture of the universe on the largest scales. Imagine a spider's web built on an almost inconceivable scale, or the neural network of a cosmic brain. The clusters of galaxies themselves sit at the dense intersections of this web, like glittering pearls strung along invisible filaments of dark matter. These filaments, which can stretch for hundreds of millions of light years, form the scaffolding of the cosmos, weaving through space and connecting cluster to cluster. Between these great walls and filaments lie the opposite extreme, colossal voids. These are the cosmic deserts, regions of space that are almost entirely empty of galaxies, spanning hundreds of millions of light years across. The contrast is breathtaking. The universe is not a uniform soup, but a highly structured tapestry of dense nodes, sweeping filaments, and vast, empty nothingness. This entire magnificent structure, from the richest cluster to the most barren void, owes its existence to the gravitational influence of dark matter, which began collapsing first, drawing the normal matter along for the ride and creating the blueprint for everything we see. The process of observing and studying these clusters provides some of the most stunning visual evidence in all of astronomy. Telescopes like Hubble give us the iconic, deep-field images that reveal thousands of galaxies within a cluster, a dizzying collection of shapes and colors. But to understand the full picture, astronomers use a technique we touched on earlier, multi-wavelength observations. While Hubble captures the visible light from the stars, an X-ray telescope like the Chandra Observatory sees the superheated intracluster gas, painting the space between the galaxies in a fiery glow. And then, by mapping the subtle gravitational lensing distortions, the way the cluster's immense gravity bends the light from even more distant galaxies located behind it, scientists can create a map of the cluster's total mass, revealing the otherwise invisible dark matter skeleton that holds the entire colossal structure together. When you combine these three views, you get a complete portrait of a galaxy cluster: the visible galaxies, the hot X-ray gas, and the dominant dark matter halo, all working in concert. It's a powerful testament to how modern astronomy isn't just about looking at the universe, but about seeing it in many different kinds of light to unravel its deepest secrets. These clusters are natural laboratories, allowing us to test the laws of physics under the most extreme conditions and giving us a direct window into the powerful, structure-shaping force of gravity operating on its very grandest stage. Zooming out from these colossal structures, we arrive at a number, a single, crucial value that cosmologists have been striving to pin down with ever greater precision for nearly a century. This is the Hubble constant, represented by the symbol h0, and it is, in essence, the current speedometer reading for the expansion of the entire cosmos. Its definition is elegantly simple, yet measuring it has proven to be one of the most formidable challenges in modern science. The Hubble constant tells us how fast the universe is expanding today. More specifically, for every megaparsec of distance between two galaxies, a megaparsec being a staggering 3.26 million light-years, space itself stretches, causing those galaxies to recede from each other at a certain number of kilometers every second. So, if a constant like h0 were measured to be 70 kilometers per second per megaparsec, it would mean that for every additional megaparsec you look out into space, a galaxy will appear to be moving away from us 70 kilometers per second faster. This isn't because galaxies are speeding through space on their own power, but because the very fabric between them is growing, adding more and more space over which that velocity accumulates. The quest to measure this fundamental constant should, in a perfectly understood universe, be straightforward. You take two different, highly reliable methods, apply them with painstaking care, and they should converge on the same number. But our universe, it seems, enjoys a good mystery. This brings us to one of the most exciting and perplexing developments in contemporary cosmology, the Hubble tension. Imagine two groups of the world's best chefs using the same, exact recipe to bake a cake. One group uses ingredients from a local farmer's market, the other uses ingredients sourced from a different continent. When they finish, both cakes are delicious, but they are subtly, yet undeniably, different sizes. That's the essence of the Hubble tension. We have two primary and supposedly reliable ways to measure the Hubble constant, and they are giving us stubbornly different answers. The first method looks at the ancient universe using the cosmic microwave background as its ultimate ruler. The Planck satellite, for instance, mapped the faint temperature fluctuations in this afterglow with incredible precision. By analyzing the statistical properties of these ripples, their size and distribution, cosmologists can work backwards, using our well-tested model of the early universe to calculate how fast the cosmos must have been expanding to produce exactly the patterns we see. This is like deducing the initial thrust of a rocket by carefully measuring its final, coasting trajectory. This early universe method gives a Hubble constant value of around 67 kilometers per second per megaparsec. The second method operates in our local modern universe. It relies on building what astronomers call the cosmic distance ladder. This isn't a single tool, but a series of interconnected steps. The first crucial rung involves a special class of stars known as Cepheids variables. These stars pulsate with a regular rhythm, and the wonderful property they have is that their pulsation period is directly tied to their true intrinsic brightness. By measuring how long it takes a Cepheid to brighten and dim, astronomers know exactly how luminous it truly is. Comparing this known luminosity to how dim it appears from Earth gives a direct and highly accurate measurement of its distance. These Cepheids are then used to calibrate the next rung of the ladder, which involves even brighter cosmic beacons, type I a supernova. These supernovae are the standard candles we discussed earlier. They all explode with nearly the same peak brightness. By observing Cepheids in the same galaxies that host these supernovae, scientists can precisely calibrate the supernova's true power. Then they can find these supernovae in galaxies much farther away, measure how dim they appear, and calculate vast distances across the cosmos. Finally, by measuring the redshift of these distant galaxies, they can plot the relationship between distance and recession velocity, directly yielding a measurement of the Hubble constant in the present day. This late universe approach, championed by projects like the SH0 collaboration, consistently gives a higher value, around 73 kilometers per second per megaparsec. Now, a difference of about 6 kilometers per second per megaparsec might not sound like much, but in the world of precision cosmology, it's a chasm. The error bars on each measurement, the little plus or minus ranges that represent their uncertainty, have shrunk over the years thanks to better telescopes and more sophisticated analysis. Yet the two values refuse to meet. They are decisively statistically inconsistent. This isn't a case of one being a little off, it's a firm disagreement. And that is precisely what makes it so thrilling. If it were just a simple error in someone's calculations, it would have been resolved by now. The fact that it persists even as our tools get better strongly suggests that the problem isn't with our measurements but with our model. The Hubble tension is a potential crack in the foundation of our standard model of cosmology, and through that crack we might be glimpsing entirely new physics. So what could this new physics be? The possibilities are as fascinating as they are profound. Perhaps dark energy, the mysterious force driving cosmic acceleration, isn't constant as we've assumed. Maybe its strength has evolved over time, or it interacts with matter in ways we haven't yet imagined, subtly changing the expansion history of the universe between the ancient past and the present day. Another compelling idea involves the realm of subatomic particles. What if there exists a previously unknown type of neutrino, often called a sterile neutrino, that is more massive or abundant than we thought? These ghostly particles flooding the cosmos could have altered the rate at which the early universe expanded, leaving an imprint on the cosmic microwave background that our current models don't account for. Other theorists have proposed more radical ideas, such as the existence of early dark energy, a transient form of repulsive gravity that might have existed for a brief period in the universe's infancy. tweaking the initial conditions just enough to resolve the tension. The very fact that we have to consider such exotic solutions shows just how significant this discrepancy is. It's not merely an accounting error, it's a signal from the cosmos that our understanding of its fundamental components and their evolution through time is incomplete. The Hubble tension is a cosmic puzzle box, and in trying to open it, we are being guided toward a deeper, more complete theory of everything. All of this cosmic mapping, from the local supernova to the ancient glow of the microwave background, relies on a single, profound phenomenon that acts as the universe's ultimate speedometer and time machine. This is the power of redshift, and it serves as our 11th astounding fact. The stretching of light itself is the primary tool we use to measure the vast distances of the cosmos and peer back through billions of years of time. The principle behind it is beautifully analogous to a common experience with sound known as the Doppler effect. Picture a police car racing past you on a highway, its siren blaring. As it approaches, the sound waves are compressed, pushing them to a higher pitch. The moment it passes and begins to move away, those waves are stretched out, causing the siren's pitch to drop to a deeper, lower tone. The sound hasn't changed at its source. Its perception is altered purely by the relative motion between you and the vehicle. Light waves behave in an almost identical fashion. When a celestial object, like a distant galaxy, is moving away from us, the light it emits is stretched during its long journey across the expanding cosmos. Since red light has the longest wavelengths within the visible spectrum, this stretching process shifts the light toward the red end, hence the term redshift. The critical insight from Edwin Hubble was that this redshift wasn't random. It was directly correlated with distance. The farther away a galaxy is, the more space there is between us and it that can stretch, and therefore, the greater the redshift we observe. That galaxy isn't simply flying through a static space like a thrown rock. It is, for the most part, caught in the overall flow of the expanding universe, carried along as the very fabric of spacetime stretches. The greater redshift for more distant objects is a direct measure of how much the universe has expanded during the billions of years its light has been traveling to reach our telescopes. But redshift is far more than just a cosmic speed gauge. It is also a perfect window into the past. Because light travels at a finite, though incredibly fast, speed, we never see the universe as it is right now. We see it as it was. When you look at the sun, you see it as it appeared about 8 minutes ago, the time its light takes to cross the distance to Earth. When you look at the Andromeda galaxy, you are seeing light that left there 2.5 million years in the past. Now, extend this principle to the most distant, faint smudges of light captured by the James Webb Space Telescope. These objects display such tremendous redshift that their light has been journeying for over 13 billion years. We are witnessing them not as the mature galaxies they may be today, but as they were in their cosmic infancy, just a few 100 million years after the Big Bang. The redshift of their light is the timestamp on a cosmic photograph, allowing us to literally look back in time and observe the universe during its formative years, watching galaxies assemble and evolve across the eons. For astronomers, redshift, denoted by the letter Z, has become an indispensable and precise cosmic ruler. By analyzing the spectrum of light from a galaxy, splitting its light into a rainbow of constituent colors, scientists can identify the unique chemical fingerprints of elements like hydrogen, oxygen, and silicon. These fingerprints appear as specific, recognizable patterns of dark or bright lines. In a laboratory on Earth, these patterns occur at fixed, known wavelengths. In the light from a receding galaxy, the entire pattern is shifted en masse toward longer, redder wavelengths. The amount of this shift allows for an exquisitely precise calculation of the redshift value. A small redshift indicates a relatively nearby object, while a colossal redshift tells us we are looking at one of the most distant and ancient objects in the observable universe. This tool is what allows cosmologists to construct the Hubble-Lemaitre law. the graph of velocity versus distance that defines the expansion rate of the universe. It transforms the night sky from a static, two-dimensional painting into a dynamic, three-dimensional volume with a built-in historical record, enabling us to trace the expansion history of the cosmos from the present day all the way back to its earliest transparent moments. Now, with our cosmic speedometer and time machine in hand, let's use that power of redshift to journey back further than we ever have before, to a time when the universe wasn't filled with galaxies and stars, but was an utterly alien, searingly hot, and unimaginably dense cauldron of raw energy and nascent particles. This brings us to our 12th astounding fact. In its first fleeting moments, the universe was a hot, dense soup of fundamental particles, a primordial state where not even atoms could exist. If we could rewind the cosmic clock from today, watching galaxies merge and stars wink out, we'd eventually reach a point where the entire observable universe was compressed into a volume smaller than a single atom. The temperature and density were so extreme that the familiar laws of physics as we know them began to break down, and reality was governed by a surreal, high-energy dance of the most basic building blocks of existence. To set the scene, let's pick up the story about 1 microsecond after the Big Bang. At this point, the temperature of the cosmos was a staggering several trillion degrees. The universe was not filled with gas or plasma as we understand it. It was a completely different state of matter called the quark-gluon plasma. In this frenetic environment, the fundamental particles that today are permanently locked inside protons and neutrons, quarks and gluons roamed freely. Think of it as a cosmic mosh pit of unimaginable energy. You couldn't have a proton or a neutron because the bonds provided by the strong nuclear force carried by the gluons were instantly shattered by the overwhelming thermal energy. Quarks and gluons bounced off each other in a dense, opaque soup, a reality where matter and energy were essentially interchangeable, as Einstein's famous equation, E equals mc squared, was in a state of constant, violent demonstration. As the universe continued its rapid expansion, it also cooled. After a few minutes, a monumental threshold was crossed. The temperature had dropped to just about 1 billion degrees, which was finally cool enough for the strong nuclear force to get a grip. In this brief, crucial window, known as Big Bang nucleosynthesis, quarks could finally bind together in groups of 3 to form the first protons and neutrons. This was the moment the basic seeds of atomic nuclei were born, but the universe was still far too hot for these new protons and neutrons to simply settle down. They were like dancers on a frantic dance floor, constantly colliding and fusing, only to be broken apart again by high-energy photons. However, the expansion was relentless, and the density and temperature were dropping fast. For a period of about 17 minutes, a delicate and frantic balancing act occurred. Protons and neutrons began to fuse, creating the first atomic nuclei in the history of the cosmos. The process was like a rapid cosmic assembly line. First, a proton and a neutron would fuse to form a nucleus of deuterium, which is a heavy isotope of hydrogen. This was a critical bottleneck. If deuterium nuclei formed too slowly, the whole chain would stall. But once enough deuterium existed, it could quickly collide with other protons and neutrons. Deuterium could fuse with another proton to form a light isotope of helium called helium-3, or 2 deuterium nuclei could collide to form a stable helium-4 nucleus. Trace amounts of an even heavier element, lithium-7, were also forged in these intense fires, and then, just as suddenly as it began, it was over. After about 17 minutes, the universe had expanded and cooled so much that the average energy of the particles dropped below what was needed to overcome the electrical repulsion between positively charged nuclei. The era of nucleosynthesis slammed shut, freezing the cosmic chemical composition in place. The result of this frantic 17-minute period was a universe composed of about 75% hydrogen nuclei single protons and 25% helium-4 nuclei by mass, with only tiny, trace amounts of deuterium, helium-3, and lithium. This initial recipe is arguably one of the most successful predictions of the Big Bang theory. When astronomers measure the chemical composition of the oldest, most pristine objects in the universe, stars in the halos of distant galaxies or clouds of primordial gas that have never been inside a star, they find this exact ratio, roughly 3 parts hydrogen to 1 part helium. Every other element in the periodic table, from the carbon in our cells to the oxygen we breathe and the iron in our blood, was forged much later in the nuclear furnaces of stars and in the spectacular explosions of supernova. This means that the first stars didn't form from a generic mix of gas. They ignited within a cosmos that had already been pre-processed by the Big Bang itself. The initial hydrogen-helium mixture set the stage for everything that followed. It determined how quickly the first stars could form, how brightly they would burn, and ultimately, the types of planets that could coalesce around later generations of stars. The fact that we can calculate the conditions of a 17-minute period just a few minutes after the birth of the universe, and then find the evidence for those predictions etched into the oldest stars, is a breathtaking testament to the power of the scientific method. It connects us directly to that primordial inferno, revealing that the story of our own origins and the very atoms that make us who we are began in the first few minutes of time. But to truly understand the origin of that perfectly crafted cosmic blueprint, we have to push our understanding of the beginning even further back into a realm that is almost pure theory, yet is supported by some of the most compelling evidence in all of cosmology. This brings us to a truly mind-stretching concept, our 13th astounding fact. The universe we see today is the product of an unimaginably violent growth spurt known as cosmic inflation. For all its success, the standard Big Bang model left cosmologists with some puzzling questions about the initial conditions of the cosmos, problems that seem to defy simple explanation. The first is known as the horizon problem. When we look at the cosmic microwave background radiation coming from opposite sides of the sky, we see regions that have the same temperature to an astonishing degree of precision. They are uniform to within about 1 part in 100,000. But here's the catch. According to the standard Big Bang timeline, these two regions on the opposite horizons of our observable universe were never close enough to have exchanged heat or information. There simply hasn't been enough time since the Big Bang for light or any form of influence to have traveled between them to equalize their temperature. It's as if you walked into a massive concert hall and found that every single person from the front row to the very back had chosen to wear the exact same shade of blue shirt without ever having communicated with each other. How could such perfect uniformity have been established? The second major puzzle is the flatness problem. Our measurements tell us with great certainty that the overall geometry of the universe is flat, meaning the fabric of space-time is not curved on large scales. However, for the universe to remain flat for 13.8 billion years, its initial density at the moment of the Big Bang had to be fine-tuned to an absolutely incredible degree of precision. Think of trying to balance a pencil perfectly on its sharpened tip. The slightest deviation, even by 1 part in a trillion, would have sent the universe careening into a completely different fate, either collapsing back on itself almost immediately in a big crunch or expanding so rapidly that no galaxies could ever form. The fact that we have a universe that is still so flat today after all this time suggests its initial conditions were preposterously, unnaturally perfect. These two problems, the horizon problem and the flatness problem, were major headaches for cosmologists, pointing to something missing from the story. The brilliant solution proposed in the early 1980s by physicists like Alan Guth and Andre Linde was the theory of cosmic inflation. This theory posits that a tiny, tiny fraction of a second after the beginning, somewhere around 10 to the negative 36 seconds, the universe underwent a brief but staggeringly explosive period of exponential expansion. During this fleeting epoch, the cosmos expanded by a factor of at least 10 to the 26, and possibly much more, in a span of time far shorter than a trillionth of a second. To grasp this scale, try this analogy. Imagine a single microscopic pea covered in all sorts of tiny wrinkles and irregularities. Now, in an instant far quicker than the blink of an eye, you blow up that wrinkled pea until it becomes the size of our entire planet. What would happen to those wrinkles? They would be stretched so enormously that the surface of that now giant sphere would appear incredibly smooth and flat from any local perspective. The original texture would be there, but its features would be stretched to scales far larger than anything we could perceive. This is precisely what inflation did to our infant universe. Before inflation began, the entire cosmos that we can now observe was smaller than a subatomic particle. This tiny region was able to reach a uniform temperature through ordinary physical processes because it was all causally connected. Then inflation kicked in, stretching this microscopic, smooth patch into a volume that was larger than our entire observable universe today. This explains the horizon problem with elegant simplicity. The entire sky was once a tiny, connected neighborhood that had time to even out its temperature before being blown up to a colossal size. It also solves the flatness problem effortlessly. Just as inflating a balloon makes its surface appear flatter and flatter from the viewpoint of a tiny ant living on it, the hyper-expansion of inflation stretched the fabric of space-time so dramatically that any initial curvature was ironed out, leaving us with the geometrically flat universe we measure today. But perhaps the most magnificent consequence of inflation is that it provides a direct and elegant origin story for the entire cosmic web of galaxies. The theory tells us that the vacuum of space at these incredible energies was not perfectly calm. It was fizzing with quantum fluctuations. At the quantum level, particles and energy are constantly popping in and out of existence due to the Heisenberg uncertainty principle. Inflation took these infinitesimal, random quantum jitters and, in that explosive moment of expansion, stretched them to astronomical proportions. The microscopic spots that were ever so slightly denser than average due to a quantum fluctuation became the seeds for the slightly warmer spots we see in the cosmic microwave background. These slight overdensities, now inflated to cosmic size, were the gravitational seeds around which dark matter and then normal matter would eventually gather over hundreds of millions of years to form the first stars, galaxies, and the vast filaments of the cosmic web. In a very real sense, every galaxy, every star, and every planet is a magnified fossil of a quantum mechanical tremor from the first moment of time. The largest structures in the universe owe their existence to the smallest possible fluctuations imaginable, a beautiful and profound connection between the microcosm and the macrocosm. While inflation is still a theoretical framework, its predictions of a flat, uniform universe with specific patterns of density fluctuations have been spectacularly confirmed by observations, making it the leading paradigm for understanding the very first instance of our cosmic story. This incredible framework of inflation, which so elegantly solves the major puzzles of our cosmos, might also open the door to one of the most speculative and expansive ideas in all of science, the multiverse. If the theory of eternal inflation is correct, then the explosive period of expansion that shaped our universe may not have been a one-time event. Instead, it could be an ongoing, endless process, a kind of cosmic foam where new universes are constantly bubbling into existence. In this breathtaking scenario, our entire cosmos, from the farthest quasar to the most distant galaxy in our observable horizon, would be just a single bubble in an infinite, frothing sea of other universes, each with its own unique history and perhaps even its own fundamental laws of physics. The mechanics of this are rooted in the behavior of the hypothetical field that drove inflation, often called the inflaton field. Think of this field as a kind of cosmic landscape, with hills and valleys representing different energy states. Our universe began when a tiny patch of this field got stuck on a high-energy plateau, a false vacuum state. The immense energy of this false vacuum is what powered the hyper-expansion of inflation. Eventually, that patch of the field rolled down into a lower energy valley, a process called reheating, where the energy of the inflaton field was converted into the hot soup of particles of the Big Bang. But here's where it gets truly mind-bending. According to the mathematics of eternal inflation, while our patch of space-time was settling down to form our universe, the overarching inflaton field in other regions could still be on that high-energy plateau, continuing to inflate at an exponential rate. In these eternally inflating regions, new bubbles of lower energy will spontaneously form, each one undergoing its own version of reheating and becoming a separate, self-contained universe, completely disconnected from our own. The overall metaverse, the backdrop in which this all occurs, is inflating so quickly that these bubble universes never collide or interact. They are forever isolated, islands in an endlessly generating cosmic archipelago. This leads to a profound implication. If this process is eternal, generating an infinite number of these bubble universes, then the physical constants we hold as fundamental and unchanging, the strength of gravity, the mass of an electron, the strength of the nuclear forces, might not be universal laws at all. They might simply be the local bylaws of our particular cosmic bubble. In another universe, the inflaton field might have rolled down into a different valley, resulting in a different vacuum energy, which would manifest as a different strength for dark energy. In some universes, dark energy might be so powerful that the universe tears itself apart in a big rip almost instantly. In others, it might be so weak that gravity causes a rapid big crunch before any interesting structure can form. The charge of an electron, the number of spatial dimensions, even the very existence of matter itself could be different from one bubble to the next. Most of these universes would likely be sterile, lifeless voids, where the constants are incompatible with the formation of atoms, stars, or planets. Our universe, with its seemingly fine-tuned constants that allow for complexity and life, would then not be a miraculous coincidence but a statistical inevitability. In an infinite multiverse, every possible combination of physical parameters will occur somewhere. We simply find ourselves in one of the rare, hospitable bubbles where the conditions are just right for us to exist and ponder its origins. It is crucial to emphasize that the multiverse remains a highly speculative consequence of our current theories, not an established scientific fact. We have no direct observational evidence for other universes, and by their very definition, they may reside in regions of spacetime forever beyond our causal reach. However, the concept has gained traction because it offers a potential solution to the nagging question of why our universe appears so finely tuned for life. For decades, physicists have been puzzled by the fact that if any of about a dozen physical constants were even slightly different, the universe as we know it would not exist. For instance, if the strong nuclear force were just a few % stronger, all the hydrogen in the early universe would have fused into helium, leaving no fuel for stars. If it was slightly weaker, heavy elements necessary for planets and life would never form. The multiverse idea provides a context for this fine-tuning without requiring a designer. In a vast enough ensemble of universes, a few are bound to hit the cosmic jackpot. This idea pushes the very definition of science to its limits. How can we test a hypothesis about realities that are fundamentally inaccessible? Some theorists suggest that if our universe ever collided with another bubble universe in the distant past, the immense energy of that collision might have left a unique, circular imprint on the cosmic microwave background, a cosmic bruise that we could potentially detect. Others are exploring the mathematical consistency of the theory. searching for ways to derive testable predictions about our own universe from the multiverse framework. Whether the multiverse is a profound insight into the nature of reality or a philosophical step too far remains one of the most heated and fascinating debates in modern cosmology. It represents a frontier where established physics, speculative theory, and deep philosophy collide, forcing us to confront the ultimate question of whether our reality is all there is, or merely a single page in an infinite cosmic library. When we look at those stunning Hubble Deep Field images with their thousands of galaxies shimmering in a tiny patch of sky, it's easy to get the impression that the cosmos is a crowded, bustling metropolis. The reality, however, is one of the most counterintuitive and isolating truths in all of science. For all its grandeur and seemingly filled vistas, the universe is overwhelmingly, profoundly empty. This brings us to our 15th astounding fact. When averaged across its vast volume, the universe has a density so incredibly low that it is, for all practical purposes, a near-perfect vacuum. The majestic galaxies and brilliant stars we admire are not the rule. They are the rare and fleeting exceptions, tiny, glowing islands adrift in an endless, dark, and unimaginably vast sea of nothingness. To truly grasp the scale of this cosmic emptiness, let's shrink our solar system down to a more relatable size. Imagine the Sun, a raging sphere of nuclear fusion nearly 1.4 million kilometers in diameter, is reduced to the size of a grapefruit sitting on a table in New York City. On this scale, the Earth, our entire world with all its continents, oceans, and civilizations, would be a tiny grain of sand orbiting about 10 meters away. The outermost planet, Neptune, would be a pinhead circling the grapefruit sun from over 300 meters away, roughly the length of 3 football fields. Now let's journey to the next star system, Alpha Centauri. Where would it be in our scaled-down model? You would have to take that second grapefruit and place it not in the next city, or even the next state, but all the way across the continent in Los Angeles. The sheer, staggering emptiness between these two grapefruits, representing the Sun and its nearest stellar neighbor, would contain virtually nothing but a few lonely, microscopic dust grains and the tenuous wisps of the interstellar medium. This is the true nature of our cosmic neighborhood. The solar system itself is mostly void, and the gaps between stars are exponentially more desolate. This emptiness is not just a curious fact, it is the fundamental environment in which the entire cosmic drama plays out, and it has profound implications for the universe's evolution and ultimate fate. All that empty space is the stage upon which the expansion of the universe occurs. When we say space is stretching, we are talking about this vast nothingness between galaxies growing even larger. Because galaxies are so small compared to the voids that separate them, this expansion can proceed with little resistance. There is no substantial friction, no cosmic drag to slow it down. The incredible emptiness is precisely what allows dark energy to so effectively push galaxies apart, accelerating them on their one-way journeys into the deepening darkness. It's the reason the cosmic horizon is shrinking, and it is the primary driver behind the eventual heat death we discussed earlier. In a universe that was densely packed with matter, gravity would have a much stronger grip, and the expansion would have likely slowed to a halt or reversed long ago. But our universe chose sparseness, and that choice dictates a cold, expansive, and lonely future. This realization also forces a shift in how we view the night sky. When you look up at the band of the Milky Way, you are not looking at a solid wall of stars. You are peering through a cosmic forest, but a forest where the trees are thousands of kilometers apart. The light from those stars has traveled for years, decades, and centuries across an almost perfect vacuum to finally land on your retina. The darkness between them isn't just an absence of light, it is the dominant feature of the cosmos, the true background color of the universe. Even within galaxies themselves, the emptiness is paramount. If you could take all the matter in the Milky Way, every star, every planet, every wisp of gas and dust, and smush it together into a perfectly solid blob, the resulting object would be vastly smaller than the galaxy's current majestic spiral form. The galaxy is a collection of tiny, dense knots of matter separated by light years of near-total vacuum. This omnipresent void is the canvas, and the galaxies and stars are but the faint, delicate brushstrokes upon it, a temporary and beautiful contrast against an infinite, dark backdrop. This seemingly simple, geometric fact that our universe is flat is one of the most profound discoveries in cosmology, a finding that speaks directly to the ultimate fate and fundamental nature of all reality. When we say the universe is flat, we're not talking about a two-dimensional pancake. Instead, we're describing the very fabric of space-time on its largest, grandest scale. In a flat or Euclidean universe, the classic rules of geometry we all learned in school hold true. Parallel lines will never meet, no matter how far they're extended, and the interior angles of a triangle will always add up to exactly 180 degrees. This is the geometry of an infinite plane, and if the universe is indeed flat and infinite, it means that space just keeps going forever without ever looping back on itself or curving away into nothingness. But how could we possibly measure the shape of something as vast as the entire cosmos? The answer lies in the oldest light we can see, the cosmic microwave background. This fossil radiation is our ultimate celestial surveyor's tool. Think of it like this: the tiny temperature fluctuations in this afterglow, those hot and cold spots we discussed earlier, have a characteristic size. They were imprinted by sound waves traveling through the primordial plasma, and their physical scale is determined by the speed of sound in that early universe, a known quantity. This gives us a known ruler stamped onto the sky. Now, imagine trying to measure the apparent size of this ruler from our vantage point here on Earth. The geometry of the universe acts as a giant lens. If the universe were positively curved like the surface of a sphere, that lens would act as a magnifying glass, making those hot and cold spots appear larger to us than they actually are. If the universe were negatively curved like a saddle, it would act as a demagnifying lens, making the spots appear smaller. After decades of painstaking measurements by satellites like WMAP and Planck, the result is unequivocal. Those spots appear exactly the size we expect them to be. The cosmic lens has no magnification or demagnification power at all. The universe on the largest scales is geometrically flat. This finding immediately rules out some truly fascinating, albeit fictional, possibilities. A positively curved or closed universe would be finite but without an edge, much like the surface of a balloon. In such a cosmos, if you could build a powerful enough telescope and peer out in one direction, you might eventually see the back of your own head, as light would have traveled all the way around the universe. A negatively curved or open universe would have a geometry reminiscent of a saddle, where parallel lines would diverge and the angles of a triangle would sum to less than 180 degrees. This would be an infinite universe that expands forever at an ever-accelerating rate. Our flat universe sits precisely on the knife's edge between these two dramatic alternatives, a condition that points to something extraordinary happening in the first instance of time. The flatness of the universe is not a coincidence. It is a direct prediction and a triumphant success of the theory of cosmic inflation. Recall that before inflation, the entire observable universe was a tiny, subatomic speck. In such a small region, the geometry could have had any amount of curvature, but then inflation occurred, stretching that tiny patch by an unimaginable factor. This process is analogous to taking a tiny, wrinkled crinkle from the surface of a balloon and inflating the balloon to the size of the Earth. From the perspective of an ant standing on that now vast surface, the local geometry would appear perfectly flat. Any initial curvature would have been stretched out to a scale far larger than anything we can observe. inflation didn't just make the universe smooth and uniform, it ironed out its wrinkles so completely that it left the fabric of space-time perfectly flat. The fact that our most precise measurements confirm this flatness is one of the strongest pieces of evidence we have that a period of hyper-fast inflation really did occur in the first fraction of a second of cosmic history. This geometric flatness also tells us something absolutely critical about the contents of the cosmos. According to Einstein's theory of general relativity, the geometry of the universe is directly determined by its total density, the amount of mass and energy contained within every cubic meter of space. There is a specific critical density required to make the universe flat. If the actual density were higher, the universe would be positively curved and eventually collapse. If it were lower, it would be negatively curved and fly apart. Our measurements show that the universe is flat, which means its total density must be exactly at this critical value. This is where the cosmic inventory we discussed earlier becomes so crucial. When we add up all the ordinary matter and all the dark matter we've detected through their gravity, we only account for about 32% of the critical density. The remaining 68%, the missing majority needed to make the universe flat, is the dark energy. The flatness of the universe is therefore not just a geometric curiosity. It is one of the most powerful independent lines of evidence for the existence and dominance of this mysterious repulsive force. It confirms that dark energy is not a small correction to our models, but the single largest component of the cosmic pie, the decisive factor that dictates the geometry and the ultimate destiny of everything. Now, let's bring this cosmic journey right back home to a fact that connects the grand expansion of the universe directly to our own existence. In a very real and physical sense, we are all made of stardust. This isn't just a poetic metaphor, it is the literal scientific story of our origin. Cast your mind back to the aftermath of the Big Bang, that primordial fireball we explored earlier. After the frantic first few minutes of nucleosynthesis, the universe was left with a very simple chemical composition. About 75% hydrogen, 25% helium, and a tiny, almost negligible sprinkling of lithium. That's it. There was no carbon for life, no oxygen for water, no iron for blood, no calcium for bones. The universe was a vast, boring sea of the two lightest elements, utterly incapable of building a planet, an ocean, or a single living cell. So, where did all the other 90+ elements on the periodic table come from? The answer lies in the life cycles of stars, and crucially, the expansion of the universe created the necessary conditions for this stellar alchemy to occur. The relentless stretching of space after the Big Bang did two vital things. First, it allowed the universe to cool from its initial inferno, creating pockets where gravity could begin its slow, patient work. Second, and more profoundly, it provided the ultimate gift, time. It took hundreds of millions of years for the first stars to coalesce from those clouds of pure hydrogen and helium. These were the universe's first factories, and they operated on a scale we can barely imagine. Deep within their cores, under crushing pressures and temperatures of millions of degrees, nuclear fusion performed its magic. In a step-by-step process called stellar nucleosynthesis, stars began to cook hydrogen into helium. In larger stars, as hydrogen fuel ran low, the core would contract and heat up even further, allowing helium atoms to fuse into carbon, and then carbon into oxygen, and so on, building elements like neon, magnesium, and silicon in concentric shells like the layers of a cosmic onion. The star becomes a factory, with its core acting as a forge creating ever heavier elements. But for these newly forged elements to become available for building planets and life, they had to escape the star's immense gravitational grip. This is where the most dramatic, violent, and beautiful events in the cosmos come into play: supernova explosions. For the most massive stars, this forging process continues all the way to iron. However, fusing iron doesn't release energy, it consumes it. With its energy production suddenly cut off, the star's core catastrophically collapses in less than a second, triggering a titanic rebound explosion, a supernova. The blast is so incredibly energetic that it can briefly outshine an entire galaxy. In this fleeting, unimaginable inferno, conditions become so extreme that elements heavier than iron are created, such as gold, silver, lead, and uranium. The supernova then hurls this newly enriched material, this stellar ash, far out into the surrounding interstellar space, seeding vast clouds of gas and dust with the raw ingredients for new solar systems. Our own solar system formed from such a cloud about 4.6 billion years ago. The Sun is a later generation star, and the Earth, along with every other planet, asteroid, and comet, was built from this pre-enriched cosmic debris. Every atom of carbon in every molecule of your DNA was forged in the heart of a long-dead star. The oxygen you just breathed in was created in a massive sun that exploded billions of years before our sun even ignited. The iron that carries oxygen in your blood was synthesized in the final moments before a star went supernova. Even the iodine essential for your thyroid function was likely born in the merger of two neutron stars, another spectacular event that scatters heavy elements across the galaxy. This means that the expansion of the universe was not just some distant, abstract phenomenon. It was the essential precursor that set the stage for our very existence. It provided the vast arena and the billions of years necessary for generations of stars to be born, to live out their lives, to die in spectacular explosions, and to ultimately recycle their ashes into new stars, planets, and eventually us. We are not just observers of the cosmos, we are a physical part of it, the universe itself becoming conscious, looking back at the stars and tracing our lineage back to their fiery hearts. This brings us to a concept that challenges our most fundamental experience of reality, the very flow of time. We all live with the intuitive feeling that there is a universal present moment, a now that applies to everyone and everything across the cosmos. But this sensation, our 18th astounding fact reveals, is a complete illusion. On cosmic scales, the idea of a single, shared now shatters, replaced by a fragmented and deeply personal tapestry of time, all thanks to the finite, unbreakable speed of light and the relentless stretching of space itself. Let's start with the most direct consequence of light's finite speed. When you gaze up at the star-filled night sky, you are not seeing those stars as they are at this very moment. You are looking into a living museum. The light from the star Sirius has been traveling for about 8.6 years to reach your eyes. You see it as it was when a child born then was just learning to walk. The light from the Orion Nebula is 1,300 years old, meaning we see it as it was around the time of the fall of the Roman Empire. Now extend this principle to its logical extreme. The Andromeda Galaxy, our nearest large galactic neighbor, appears to us as it was 2.5 million years in the past. When we point the most powerful telescopes at the most distant galaxies, we are witnessing their infancy, seeing light that has journeyed for over 13 billion years. This means that if an advanced civilization in the Andromeda Galaxy had a telescope powerful enough to see Earth right now, they wouldn't see you watching this video. They would see a world dominated by early hominids with no cities, no agriculture, and no recorded history. There is no single now connecting us and them. There are only thens, separated by a gulf of time that is also a gulf of space. But the plot thickens considerably when we introduce Einstein's theory of special relativity. Einstein demonstrated that simultaneity, the notion that two events occurring at the same time, is not an absolute fact of the universe, but is relative to the observer's state of motion. Imagine a flash of light occurring at the exact center of a moving train car. For a passenger sitting in the center of that car, the light will reach the front and the back walls at the same instant. Those two events are simultaneous for her, but for an observer standing on the platform as the train speeds by, the situation is different. because the back of the train is moving toward the point where the flash happened and the front is moving away from it, the light will actually reach the back wall first from the platform observer's perspective. The very same two events, light hitting the front and back walls, are not simultaneous for him. This isn't a trick of perception, it's a fundamental property of space-time. There is no privileged God's eye view to declare which events are truly now for the entire cosmos. Your now is intimately tied to your path through the universe. Now, weave the expansion of the universe into this relativistic tapestry, and the concept of a universal present completely unravels. The stretching of space itself creates additional, profound complications for defining simultaneity across cosmic distances. Because space is not static but dynamically growing, the very definition of now for a distant galaxy becomes entangled with how we define our measurements in an expanding cosmos. Cosmologists use something called the cosmological time coordinate, which slices space-time in a way that is commoving with the overall expansion. In this framework, we can define a surface of constant time, a kind of cosmic now that connects us with distant galaxies. But here's the crucial point. This is a definition, a convenient mathematical choice, not an absolute physical reality. An observer in a galaxy racing away from us due to the Hubble flow would define their own different surface of simultaneity. An event that we label as happening now in a galaxy 10 billion light-years away might be placed in the past or the future on their cosmic clock. The expansion of space ensures that there is no way to synchronize clocks across the vast intergalactic voids in any absolute sense. The fabric of reality itself is stretching, and with it, any hope of a single, universal present moment stretches into irrelevance. This leads to a truly mind-bending implication for the universe's history. We often talk about the Big Bang as happening everywhere at once 13.8 billion years ago. But if there is no universal now, how can we even define what at once means? The Big Bang wasn't an explosion in space from a point, it was the rapid expansion of space itself. Because of this, the moment of the Big Bang isn't a point in our universe's past that we can look back toward from a privileged present. Instead, it lies in the past for every point in the universe. It is more accurate to think of the Big Bang as the moment when the distance between every point in the observable universe was zero, and the density and temperature were infinite. This condition applies to the entire cosmos, but it doesn't happen at a single instant of a universal clock. Our now and the Big Bang are connected by our own unique past light cone, the path that light has taken to reach us. Every observer in the cosmos has their own past light cone that converges back to the Big Bang in their own reference frame. The beginning of time itself is a personal frontier, not a shared starting line. So, what does this mean for our place in the cosmos? It forces a profound and humbling perspective shift. We are not passive observers watching a universe unfold on a single, giant movie screen with a shared timeline. Instead, each of us, and indeed every conscious being anywhere in the universe, carries their own personal projection of reality, their own unique now, built from the cascade of light and information that has finally reached them after epic journeys across space and time. The universe you perceive is a carefully constructed mosaic of the past, a patchwork of thens from different epochs and different distances. The majestic spiral of Andromeda, the fiery birth of a distant star, and the echo of the cosmic microwave background are all presented to you simultaneously, yet they are snapshots from billions of years apart, presented on your celestial view screen only because their light has managed to complete its long journey to your eyes at this particular moment in your life. Your present is a collage of the cosmos's deep past, and the true, unified present of the universe remains forever beyond our grasp, a hidden layer of reality whose full, synchronous majesty we can only infer through mathematics and imagination, but never directly experience. This brings us to a phenomenon that allows us to feel the very vibrations of the cosmos, a direct detection of the universe's dynamic nature that goes beyond light. Our 19th astounding fact reveals that gravitational waves are real ripples in the very fabric of space-time itself, traveling across the cosmos at the speed of light. For centuries, our understanding of the universe was built entirely on light. From the visible rays our eyes can see to the invisible X-rays and radio waves our telescopes detect. But light can be blocked, absorbed, or scattered. Gravitational waves are different. They are a distortion of the stage upon which the cosmic drama plays out, and they pass through matter almost completely unimpeded, carrying with them a pure, unadulterated story of the most violent events in the universe. The story of their discovery begins with Albert Einstein. In 1915, his theory of general relativity completely redefined our concept of gravity. Instead of a mysterious force acting at a distance, gravity was the result of mass and energy warping the four-dimensional fabric of spacetime. Think of spacetime as a taut, flexible rubber sheet. Place a heavy bowling ball in the center and it creates a deep dimple. A nearby marble will roll around the bowling ball, not because of a direct pull, but because it's following the curved path of the sheet. Einstein's equations predicted that if massive objects accelerated, not just moved, but changed their speed or direction violently, they would send out ripples through this space-time fabric, much like a spinning skater suddenly throwing their arms out would send vibrations through the ice. For decades, this was considered a purely theoretical curiosity. The distortions produced by even the most massive astronomical objects were calculated to be infinitesimally small, far beyond any conceivable technology to measure. Einstein himself wavered on whether they were physically real or just a mathematical artifact. The quest to prove their existence became one of the great challenges of 20th century physics, culminating in one of the most stunning scientific achievements of our time. On September 14, 2015, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct detection. The signal, christened GW150914, was a distinctive chirp, a rapid increase in the frequency and amplitude of the wave that lasted just 0.2 of a second. When scientists analyzed this cosmic fingerprint, they found its source, a pair of black holes, one about 36 times the mass of the Sun and the other 29, locked in a final, fatal dance about 1.3 billion light-years away. In the last frenetic moments before they merged into a single, more massive black hole, they whipped around each other at nearly half the speed of light, pumping enormous amounts of energy into the fabric of spacetime in the form of gravitational waves. That fleeting 0.2 of a second event released more power in gravitational waves than all the light emitted by every star in the observable universe at that same moment. The detection was not just a confirmation of Einstein's genius, it was the opening of an entirely new sense with which to perceive the cosmos. So, what exactly happens when a gravitational wave passes through you? The effect is a rhythmic stretching and squeezing of space itself. Imagine a gravitational wave traveling outward from a cosmic collision, with its energy concentrated in two perpendicular directions. As the wave passes through a region of space, it will stretch that space in one direction while simultaneously squeezing it in the direction at a right angle. Then, as the wave oscillates, it reverses the process, squeezing where just stretched and stretching where just squeezed. If you were floating in space near such an event, you wouldn't feel a thing because everything, including your own body and the rulers you might use to measure distance, would be stretched and squeezed in the same way. This is why detecting them is so extraordinarily difficult. LIGO works by using laser beams traveling down 2-4-kilometer-long arms arranged in an L shape. When a gravitational wave passes by, it minutely changes the length of one arm relative to the other by a distance thousands of times smaller than the nucleus of an atom. By monitoring the interference pattern of the lasers with almost unimaginable precision, LIGO can detect this tiny, rhythmic warping, translating it into a sound that we can hear the chirp of colliding black holes. This new sense of hearing the universe has revolutionized astronomy. Before gravitational wave astronomy, the cosmos was a silent movie. Now we have the soundtrack. This allows us to observe phenomena that are completely dark to traditional telescopes. The merger of two black holes, for instance, emits no light whatsoever. It is a purely gravitational event. Without LIGO, we would have no way of knowing it even happened. But with our new ears, we can not only hear these events but also measure the properties of the black holes involved, their masses, their spins, and their distance from us. This is providing the first direct census of black holes in the universe, revealing a population that was previously hidden from our view. Furthermore, in 2017, a monumental event occurred when LIGO and its European counterpart, Virgo, detected gravitational waves from the collision of two neutron stars. Crucially, this event was also seen by telescopes across the electromagnetic spectrum, from gamma rays to radio waves. This first ever multi-messenger observation allowed astronomers to pinpoint the source in a distant galaxy and watch in real time as the collision forged heavy elements like gold and platinum, confirming that these cataclysmic events are the universe's primary cosmic forges for the heaviest elements. Gravitational waves are therefore more than just a new tool. They are a fundamental part of a new, integrated approach to understanding the cosmos, allowing us to probe the most extreme environments where gravity is king and the laws of physics are pushed to their absolute limits. While the idea of a universe expanding so fast that it creates an ultimate limit to what we can see might feel like science fiction, it is a direct and inevitable consequence of the dark energy-dominated cosmos we live in. This brings us to our 20th astounding fact. The accelerating expansion of the universe is actively creating a cosmic event horizon, a boundary in time that is forever cutting us off from a vast portion of reality. We are used to the idea of a horizon here on Earth, the literal point where the distant landscape dips below the curve of our planet, hiding what lies beyond. In a similar way, the cosmos has a horizon, but its cause isn't the curve of a planet. It's the relentless stretching of space-time itself, driven by dark energy. Imagine a galaxy so profoundly distant that the space between us and it is expanding faster than the speed of light. Now, this doesn't violate Einstein's law that nothing can move through space faster than light, because it is space itself that is growing, carrying the galaxy along for the ride. A photon of light emitted from that galaxy toward us would be like a swimmer trying to cross a river that is widening faster than they can swim. Despite racing toward us at the ultimate cosmic speed limit, the photon would find itself fighting a losing battle, its progress continually undone by the creation of new space ahead of it. It is destined to never complete its journey. That galaxy and every event occurring within it from this moment forward is now and forever beyond our view, receding into a permanent, inaccessible past. This cosmic event horizon shares a name with the infamous boundary around a black hole, but the nature of the two is fundamentally different. A black hole's event horizon is a barrier in space. It's a one-way surface that, once crossed, seals your fate, preventing any information from escaping the black hole's gravitational grip. The cosmic event horizon, however, is a limit in time. It's not a physical wall you could bump into. It is a gradually evolving threshold defined by the expansion history of the universe. Every day, as the expansion continues to accelerate, this horizon tightens its grip. Galaxies that are today just on the edge of our observable limit will, in the future, cross this invisible boundary. Their light, which is currently en route to us, will be the last we ever see from them. Once that final photon arrives, their story in our sky comes to an absolute end. They don't vanish in a flash, they simply fade to black, their light redshifting into undetectable wavelengths as they are carried away by the Hubble flow into the eternal darkness. This process is happening all around us, creating a sphere beyond which the universe is not just dark, but fundamentally unknowable. The philosophical implications of this are staggering. It means that the universe has already enacted a form of cosmic censorship, placing vast realms of existence forever outside the reach of our knowledge. We can speculate about what lies beyond our horizon, perhaps infinite more galaxies, stars and planets, or even other, stranger forms of matter and energy, but we can never receive any data, any signal, any confirmation. Any event happening in those regions today, be it the birth of a star, the collision of galaxies, or the rise and fall of civilizations, is information that is causally disconnected from our pocket of the cosmos. Our entire scientific endeavor is based on the principle of observable, testable evidence. The cosmic event horizon establishes a permanent and unbreachable limit to that endeavor, a gentle reminder from the universe that some mysteries are not meant to be solved. It confines our entire history from the Big Bang to the far future to a single, shimmering but finite bubble of awareness. The grand cosmic narrative we are piecing together is, therefore, only a local story, a biography of our own observable universe, while the true, full extent of reality remains an eternal secret. But this grand cosmic web, with its majestic galaxies and vast voids, didn't just appear out of nothing. Its origins trace back to a realm of physics so small and strange that it seems completely disconnected from the scales of galaxy clusters and superclusters. This brings us to a fact that beautifully ties together the very large and the very small. All the cosmic structure we see today was seeded by random quantum fluctuations in the first instance of time. To understand how this works, we need to venture into the bizarre world of quantum mechanics, where the very concept of nothing loses its meaning. In the quantum vacuum, empty space isn't truly empty. Due to the Heisenberg uncertainty principle, there is a fundamental fuzziness to reality at the smallest scales. Particles and their antimatter partners spontaneously pop into existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and vanishing. This constant, frantic activity means that on the quantum level, there is always a tiny, unpredictable jitter in the energy density of a region, a fluctuation. Now recall the theory of cosmic inflation, that violent hyper-expansion of the universe in its first fraction of a second. This period didn't just stretch the universe to a vast size, it also acted as a cosmic amplifier for these quantum jitters. Imagine a tiny, subatomic region where, by pure quantum chance, there is a minuscule overdensity, just a few more virtual particles popping into existence than usual. Right next to it, another region might have a corresponding underdensity. Under normal circumstances, these fluctuations would be utterly insignificant and would vanish almost instantly. But inflation was not normal. It grabbed these infinitesimal quantum ripples and stretched them across the cosmos, freezing them into the very fabric of space-time and magnifying them to macroscopic proportions. The tiny overdensities and underdensities that were once smaller than a proton were inflated to scales of millions of light years. They became the first subtle variations in the density of the universe, the very first hint of structure in what was an otherwise perfectly smooth and uniform sea of hot plasma. The evidence for this quantum origin is written across the sky in the cosmic microwave background. The subtle hot and cold spots we see in that afterglow map are not random noise. They are the direct, fossilized imprint of those amplified quantum fluctuations. The slightly warmer regions correspond to areas that were a tiny bit denser, and the cooler spots to areas that were a tiny bit more rarefied. This pattern is the universe's birthmark, a snapshot of the quantum foam from which it sprang. Without these initial ripples, gravity would have had nothing to work with. The universe would have remained a featureless, boring expanse with no gathering points to collapse into stars and galaxies. The existence of these fluctuations provided the essential gravitational seeds. Over the next several 100 million years, the relentless pull of gravity took over. The regions of slightly higher density, reinforced by the gravitational pull of dark matter, had a tiny advantage. They pulled in a little more gas from their surroundings, which made them slightly denser, which in turn increased their gravitational pull, allowing them to attract even more matter. It was a slow, cosmic feedback loop of growth. This process of gravitational collapse and clustering transformed those faint quantum whispers into the roaring symphony of structure we see today. The densest knots grew into the first stars, which gathered into proto-galaxies. These galaxies then merged and clustered, drawn together along the invisible filaments of dark matter, eventually forming the great walls and nodes of the cosmic web. The vast voids are the complementary part of this story. They are the regions that lost the gravitational tug of war. Their matter slowly drained away over billions of years to feed the growing structures elsewhere. This means that the distribution of galaxies we map with our telescopes, the location of every great cluster, and the position of our own Milky Way are not random. They are the end result of a chain of causality that stretches back over 13 billion years to a set of random quantum events in the first moment of time. The grand architecture of the cosmos, therefore, has its roots in the unpredictable, probabilistic heart of quantum mechanics. It's a profound connection that suggests the universe itself may be the ultimate quantum experiment, with the largest structures we can observe owing their existence to the smallest and most fleeting of phenomena. Now, as we've mapped the cosmic web and listened to the echoes of gravitational waves, we need a way to take a precise measurement of this grand structure, a cosmic ruler etched into the very distribution of matter itself. This brings us to a subtle but incredibly powerful tool in the cosmologist's toolkit, our 22nd astounding fact. Baryon acoustic oscillations are a frozen echo from the dawn of time, a standard ruler that allows us to chart the expansion history of the universe with remarkable precision. To understand what these are, we need to journey back once more to the universe's first few 100,000 years, to that searing, opaque plasma of photons, electrons, and atomic nuclei, the latter known collectively as baryons. In this dense, hot soup, a fascinating tug of war was taking place. On one side, you had the relentless pull of gravity, trying to clump the baryons together into denser regions. Pushing back with immense force was the pressure of the radiation, primarily from the countless photons that were constantly bouncing off the free electrons, refusing to be compressed. This competition created sound waves, not sound as we hear it, but colossal, spherical pressure waves that rippled outward through the primordial plasma at a significant fraction of the speed of light. Imagine dropping a single, incredibly dense pebble into this cosmic pond. Gravity would pull the surrounding material inward, but as it compressed, the radiation pressure would build up and violently push it back out, creating an expanding shell of overdense material. This shell would then be pulled back in by gravity, only to be pushed out again, creating a rhythmic oscillation, a ringing, if you will, across the entire early universe. This wasn't happening from a single point, but from every single one of those tiny quantum fluctuations we discussed. Each slight overdensity acted as a source for its own expanding spherical wave. Then, at the moment of recombination, when the universe cooled enough for atoms to form and the cosmic microwave background was released, a crucial thing happened. The fog lifted and the photons streamed away. Suddenly, the main source of outward pressure vanished. The baryons, no longer being pushed by the radiation, were frozen in place. The waves simply stopped propagating. What was left was a universe imprinted with a specific characteristic scale, the distance that a sound wave could travel from the beginning of the universe up until that moment, about 380,000 years after the Big Bang. This distance became a permanent fossil, a standard ruler stamped onto the cosmos. In the distribution of matter, it manifested as a slight preference for galaxies to be separated by this specific distance. You can think of it as the universe having a faint, ghostly grid, where the spacing between the lines is exactly the radius of that last frozen sound wave shell, which measures about 500 million light-years across today. So how do we use this fossil as a ruler? The principle is beautifully straightforward. Imagine you have a ruler of a known length, say 30 centimeters. If you hold it close to your face, it appears large. If you hold it at arm's length, it appears smaller. Astronomers do the same thing with the BAO scale. By conducting massive galaxy surveys like the Sloan Digital Sky Survey or the Dark Energy Survey, they can create three-dimensional maps of the universe, plotting the positions of millions of galaxies. Within this vast cosmic cartography, they use sophisticated statistical methods to look for that preferred separation distance between galaxy pairs. They are essentially searching for the faint, statistical echo of those ancient sound waves in the large-scale structure. Once they identify this scale in their map, they measure its apparent size. Then, by comparing this apparent size to its known true size, the 500 million light-year standard ruler, they can calculate the distance to that particular slice of the universe with incredible accuracy. It's a direct geometric measurement of cosmic distance, independent of the brightness of stars or the vagaries of supernova. This is where its power to probe dark energy truly shines. By measuring the BAO scale at different redshifts, which means looking at different eras in cosmic history, astronomers can trace how the expansion rate of the universe has changed over billions of years. When they measure the BAO ruler in a region corresponding to the universe 9 billion years ago, they find it has one apparent size. When they measure it in a more recent, closer region, they find a different apparent size. This changing apparent size directly reveals how much the universe has stretched in the time between those two epochs. It provides a direct, clean measurement of the expansion history, h of z, showing us how the Hubble constant has evolved. The data from these BAO measurements provides one of the strongest and most robust confirmations of the accelerating universe. It shows unequivocally that the expansion was slower in the past and only began to accelerate more recently, a finding that fits perfectly with the presence of a dominant dark energy. The fact that this method, which relies on the geometry of the large-scale structure, agrees so perfectly with the results from distant supernova and the cosmic microwave background gives us tremendous confidence that we are on the right track. It's a crucial cross-check, a separate line of evidence, all pointing toward the same startling conclusion about the fundamental nature of our cosmos. If you could place a cosmic thermometer into the depths of intergalactic space and take a reading, it would show a temperature of about 2.7 degrees above absolute zero, a chill maintained by the faint, omnipresent glow of the cosmic microwave background. But that number is not a constant, it is a falling one. This slow, inexorable cooling is a direct and unavoidable consequence of the universe's expansion, bringing us to a fact that frames the ultimate destiny of all things. The universe is not only expanding, but it is also getting colder and darker on a one-way journey toward a state of profound equilibrium known as the heat death. The vibrant, structured cosmos we inhabit is a temporary phenomenon, a brilliant but fleeting flash of activity nestled between the fiery violence of the Big Bang and the unimaginably long, silent winter that lies ahead. The driving principle behind this chilling fate is one of the most fundamental in all of physics, the second law of thermodynamics. This law states that the total entropy or disorder of a closed system always increases over time. Think of entropy as a measure of how spread out and useless energy has become. A useful analogy is a steaming hot cup of coffee left on a table in a cool room. Initially, all the heat energy is concentrated in the cup, a state of low entropy that can be used to do work like powering a tiny steam engine. But over time, that heat naturally spreads out, dissipating into the room until the coffee and the air reach the same lukewarm temperature. The energy hasn't disappeared, but it has become so uniformly distributed that it can no longer be harnessed to perform any meaningful task. The system has reached a state of maximum entropy, a bland and static equilibrium. Now imagine that the room itself is not a fixed size, but is constantly, rapidly growing larger. This is exactly what is happening to our universe. The expansion of space is the ultimate agent of dilution, actively and relentlessly spreading energy thinner and thinner across an ever vaster volume. We can witness this cosmic cooling in real time by observing the most ancient light we can see. The cosmic microwave background, which we first encountered as the afterglow of the Big Bang, started its journey as visible light, blazing at a temperature of around 3,000 degrees Celsius. But over the past 13.8 billion years, the relentless stretching of space has stretched the wavelengths of those photons, redshifting them down into the microwave part of the spectrum and cooling them to their current, frigid 2.7 degrees above absolute zero. This is not a one-time event, it is an ongoing process. As the expansion continues, this fossil radiation will be stretched even further, its temperature inching closer and closer to absolute zero. In a future trillions of years from now, the CMB will have redshifted so dramatically that it will be utterly undetectable, its energy completely diluted by the immensity of space. The last remnant of the universe's hot beginning will have effectively vanished from the sky, leaving behind only the blackness of empty space and the faint, cold points of dying stellar embers. This cooling extends to the very machinery of creation itself, the stars. The universe is currently in a kind of stellar golden age, a period where sufficient gas exists to collapse under gravity and ignite the nuclear furnaces that light up the cosmos. But this is a finite resource. As galaxies continue to drift apart and the remaining gas clouds are either consumed by star formation or blown away by supernova, the rate of star birth will plummet. The last stars to form will be small, dim red dwarfs, which fuse their hydrogen fuel at a much more leisurely pace. They will glow for trillions of years, far longer than the current age of the universe, but even their immense lifetimes are finite. One by one, they too will eventually exhaust their fuel, cooling into inert balls of helium known as black dwarfs. Larger stars will meet more dramatic ends as white dwarfs, neutron stars, or black holes, but these too are not eternal. Over timescales so vast they defy human comprehension, even the protons and neutrons that make up all atomic matter are predicted by some theories to decay, dissolving the very bedrock of planets, asteroids, and stellar remnants into a thin soup of radiation and subatomic particles. The era of stars, of galaxies, of any concentrated source of light and heat will come to a permanent close. This leads us to the ultimate destination of this journey, the heat death itself. It is a state of maximum entropy for the entire cosmos. In this distant epoch, the universe will be a vast, nearly perfect vacuum. The temperature will be uniform everywhere, just a fraction of a degree above absolute zero. With no temperature differences, no hot spots or cold spots, no dense regions or empty ones, no work can be done. Energy will be present, but it will be so perfectly and uniformly smeared across the infinite expanse that it will be completely useless. It will be a universe without change, without process, and without the possibility of any form of organized complexity. The cosmos will be dark, silent, and cold, having traded the brilliant, dynamic chaos of its youth for the absolute, static order of its final state. This is the ultimate consequence of the expansion we have been exploring throughout this video, a stark and sobering contrast to the unimaginable heat and density of the Big Bang. It is a fate determined not by a dramatic collapse or a violent rip, but by a slow, irreversible fading, a descent into an equilibrium from which there is no return, a final, permanent silence in the grand narrative of existence. Just when cosmologists thought they had a firm grasp on the large-scale structure of our universe, a truly peculiar anomaly emerged from the most precise maps we have of the cosmic microwave background, an enigma so provocative it has earned a rather dramatic nickname, the axis of evil. This isn't about some cosmic force of darkness, but rather a strange and unexpected pattern in the ancient light that blankets the sky. The story begins with the cosmological principle, one of the most foundational assumptions in all of modern cosmology. This principle states that on the very largest scales, the universe is both homogeneous and isotropic. Homogeneous means the universe has a fairly uniform distribution of matter. No single spot is special or uniquely dense. Isotropic means it looks the same in every direction you look. There is no preferred orientation or central axis. This idea is the bedrock upon which we build our models of cosmic evolution, from the Big Bang to the formation of galaxies. It's why we feel confident that observers in a distant galaxy would see a universe roughly similar to our own, with no grand, overarching structure pointing a finger at one particular location in space. But the axis of evil, if it is real, throws a wrench into this elegant assumption. When scientists with the Wilkinson microwave anisotropy probe and later the Planck satellite created their exquisitely detailed maps of the cosmic microwave background, they began to notice something odd. The fluctuations in temperature, those tiny hot and cold spots that are the blueprints for galaxies, weren't entirely random. On the very largest scales, patterns stretching across billions of light years, there appeared to be a curious alignment. It was as if the cosmos had a subtle preferred direction, a kind of ghostly axis running through space. Some of the largest warm spots and cool voids seemed to line up in a way that shouldn't happen by chance in a truly isotropic universe. Even more strangely, this apparent axis seemed to be aligned, of all things, with the plane of our own solar system. This is the part that really makes scientists uncomfortable, because it immediately raises the red flag of a potential systematic error. The last thing you want to discover is that your profound insight into the nature of the cosmos is actually just an artifact of how your telescope is pointed, or how dust in our own galactic backyard is affecting the measurements. Naturally, the scientific community has split into camps regarding this bizarre finding. The most conservative, and many would argue most likely, explanation is that the axis of evil is simply a statistical fluke. When you look at any random set of data, especially a map as complex as the CMB, you are bound to find some patterns that look significant just by sheer chance. It's the cosmic equivalent of seeing a face in the clouds. Your brain is wired to find patterns even where none truly exist. Proponents of this view point out that when you apply rigorous statistical tests, the significance of the alignment diminishes. They argue we are simply seeing a classic case of a posteriori reasoning, noticing a pattern first and then assigning it importance, rather than predicting it from a theory. Other researchers have tirelessly hunted for a more mundane cause, a systematic error in the data processing. Could residual radiation from our own Milky Way galaxy, which had to be meticulously subtracted from the Planck data, be leaving a faint, structured imprint that mimics this axis? Or perhaps it's an issue with the way the spacecraft scanned the sky, inadvertently introducing a subtle directional bias. Despite years of intense scrutiny, no one has yet been able to definitively pin the anomaly on a single, convincing error, which is precisely what keeps the mystery alive and so tantalizing. This leaves the third and most thrilling possibility, that the axis of evil is a genuine feature of the universe, a real clue that our standard cosmological model is incomplete. If this alignment is not a fluke or a mistake, then the cosmological principle in its simplest form would be violated. Our universe would not be perfectly isotropic. It would have a preferred direction on the largest scales, a cosmic north. This would be a revolution on par with the discovery of dark energy. What could possibly cause such a thing? Theorists have put forward some wildly speculative but fascinating ideas. Perhaps our universe is not the only one. Maybe it collided with another bubble universe in the distant past during the inflationary epoch, and the shock wave from that collision imprinted a directionality onto our cosmos. Or maybe the fabric of spacetime itself has a very subtle intrinsic anisotropy, a fundamental graininess that only becomes apparent when we look at the universe as a whole. Another idea involves the influence of a vast, unseen superstructure far beyond our observable horizon, whose immense gravitational pull is subtly tugging on our entire local universe, creating a discernible drift in the cosmic background. While these ideas sound like science fiction, they are the kinds of bold hypotheses scientists are forced to consider when faced with persistent, unexplained data. The axis of evil stands as a quiet but persistent reminder that for all we have learned, the universe may still be holding onto its deepest secrets, challenging us to look deeper and think harder about the true, and perhaps stranger, nature of reality. And so we arrive at the ultimate frontier of sight, the final, impassable barrier in our observable cosmos. This is the surface of last scattering, a shimmering wall of fire that marks the absolute limit of what we can see with light. Imagine trying to peer into a room by looking through a dense, swirling fog so thick that you can only make out the wall closest to you, glowing with a uniform, blinding light. This is our situation with the early universe. Before this moment, about 380,000 years after the Big Bang, the cosmos was not a transparent void but an opaque, searing plasma, a roiling soup of free electrons, protons, and photons. In this dense fog, light particles couldn't travel in a straight line for more than a tiny fraction of an inch before bouncing off a free electron, trapped in a constant, frenetic pinball game. The universe was essentially a brilliant, featureless glow, and if any observer could have existed then, their entire world would have been this impenetrable, uniform blaze. The moment of last scattering was the universe's great clearing. As expansion continued, the temperature of the cosmos cooled just enough, to about 3,000 degrees Celsius, for a monumental shift to occur. Electrons, which had been zipping around freely, were finally moving slowly enough to be captured by protons, forming the first stable, neutral hydrogen and helium atoms. In an instant, the cosmic fog lifted. The free electrons that had been scattering the light were now bound up inside atoms, and the photons, which had been trapped for eons, were suddenly set free. These photons, released from their plasma prison, began their epic journey across the expanding universe, and it is that very first flash of liberated light that we detect today as the cosmic microwave background. The surface of last scattering is not a physical surface like the shell of an egg. It is a moment frozen in time, a spherical layer that exists at a distance of about 46 billion light-years in every direction, corresponding to that specific instant when the universe became transparent. We are, in effect, at the center of a colossal, glowing sphere, looking out at its inner surface in all directions, and what we are seeing is the afterglow of creation itself. This wall is the ultimate time capsule, but it is also the ultimate barrier. It represents the dividing line between the observable and the unobservable. We simply cannot use light to see any further back in time. Peering beyond this wall is like trying to see through a brick wall. The universe before that moment was so dense and hot that it was completely opaque to electromagnetic radiation. Everything that happened in the first 380,000 years of cosmic history, from the frantic formation of the first atomic nuclei in the first few minutes all the way back to the inflationary epoch and the very birth of spacetime, is hidden from our direct view. This period, often called the Dark Ages of the early universe, is a realm accessible only through theoretical physics and the indirect fingerprints it left on the universe that followed. We can model it, we can predict its consequences with stunning accuracy, but we can never directly witness it with our telescopes. The light from those earlier events was scattered into oblivion, its information lost forever to the primordial plasma. This profound limit, however, has not stopped scientists from devising ingenious ways to probe the hidden era. While photons cannot tell us the story, other messengers might. The faint gravitational waves that ripple through the fabric of space-time, for instance, are immune to the opacity of the plasma. They were generated in the violent chaos of the universe's first moments and traveled through the dense plasma unimpeded. Future observatories hope to detect these primordial gravitational waves, which would carry a clean, undistorted signal from a time far earlier than the surface of last scattering, potentially allowing us to hear the echoes of cosmic inflation itself. Furthermore, the detailed patterns in the cosmic microwave background itself serve as a fossil record. By studying the subtle variations in temperature and polarization with incredible precision, cosmologists can work backwards, using the laws of physics to infer the conditions that must have existed in the first fraction of a second after the Big Bang, testing our theories of inflation and particle physics at energies far beyond what any terrestrial collider could ever achieve. So, as we reach this final, dazzling fact in our journey, we are confronted with a beautiful and humbling truth. The surface of last scattering is both an end and a beginning. It is the end of our direct observational reach, the final page of the cosmic history book that is written in light. Yet, it is also the beginning of the structured universe we know. It was the moment the cosmos became transparent, setting the stage for the darkness to condense into the first stars and the first galaxies. It marks the transition from a seamless, fiery unity to a reality of distinct objects of structure and form. Gazing at this wall, we are looking at the universe's own birth certificate, a final, radiant fact that reminds us of both the incredible power of our curiosity to reach back to the very dawn of time, and the fundamental limits that the cosmos itself has placed on our vision, forever guarding the mysteries of its own explosive origin. And so our journey through the cosmos draws to a close, a voyage that has taken us from the very fabric of space-time to the ultimate fate of all existence. We've witnessed how the universe is not a static backdrop but a dynamic, expanding entity, accelerating its growth under the influence of a mysterious force we call dark energy. This unseen driver, comprising a staggering 68% of everything, is relentlessly pushing galaxies apart, steering the cosmos toward a cold, dark, and lonely future known as the heat death. Alongside it, we've encountered the cosmic scaffolding of dark matter, an invisible substance that makes up 27% of the universe, whose gravitational embrace holds galaxies together and sculpted the large-scale structure of reality from the primordial darkness. These two shadowy constituents, dark energy and dark matter, together compose 95% of the cosmos, a humbling reminder that the ordinary matter we see and are made of is just a fleeting afterthought in the grand cosmic inventory. Our exploration took us back to the very beginning, to a hot, dense state where the universe was smaller than an atom, and through the brilliant theory of cosmic inflation, which solved profound puzzles by stretching a quantum speck into a macroscopic cosmos. We learned that the magnificent cosmic web of galaxies, with its vast clusters and immense voids, owes its existence to random quantum fluctuations, tiny jitters in the fabric of reality that were amplified to cosmic proportions in the first fraction of a second. This incredible connection between the quantum world and the largest structures we can observe reveals a universe born from uncertainty and chaos, yet evolving with a precise and elegant set of physical laws. We've peered at the fossilized light of the cosmic microwave background, heard the chirp of colliding black holes through gravitational waves, and confronted the limits of our own perception with the realization that there is no universal now. Each fact has peeled back a layer of mystery, only to reveal deeper, more profound questions waiting just beneath the surface. What does this all mean for us, here on our tiny, fragile planet, orbiting an average star in a quiet corner of a typical galaxy? It means that we are an integral part of this grand cosmic story. The very atoms that form our bodies were forged in the hearts of long-dead stars, scattered across the galaxy by supernova explosions, and eventually assembled into the complex chemistry of life. We are the universe becoming conscious of itself, capable of looking out at the vast expanse and not only witnessing its history but also contemplating its future. The pursuit of these mysteries, the nature of dark energy, the identity of dark matter, the true geometry of the cosmos, is not merely an academic exercise. It is one of humanity's greatest and most profound adventures, a testament to our insatiable curiosity and our relentless drive to understand our place in the grand scheme of things. In grappling with these cosmic truths, we connect with generations of thinkers who have looked up at the stars and dared to ask, why? As we conclude, I want to turn the question over to you. Among these 25 astounding facts, which one reshaped your understanding of reality the most? Was it the sheer emptiness of the cosmos, the accelerating expansion driven by dark energy, or perhaps the humbling realization that we are made of stardust? Share your most mind-blowing takeaway in the comments below. I read every single one and love hearing your perspectives. If this journey through the expanding universe has ignited your curiosity, consider subscribing to the channel. We're just getting started, and there are so many more wonders to explore, from the enigmatic nature of black holes to the search for life beyond Earth. Thank you for joining me on this incredible expedition to the edges of space and time. Keep looking up and never stop wondering.